Look up at the night sky. For most of human history, those pinpricks of light were just that, distant, unknowable specks, subjects of myth and mystery, but utterly disconnected from our daily existence. But what if that view is an illusion? What if the future of our world, the solutions to our greatest challenges, and the next chapter of the human story are not hidden here on Earth, but are silently waiting for us, written in the fabric of the cosmos itself? Imagine for a moment that our planet is not an isolated island, but a single room in a vast, unexplored mansion. We've been so focused on arranging the furniture in this one room that we haven't yet dared to open the doors to the halls beyond. Halls that could hold the blueprints for everything from unlimited energy to cures for disease. This is not science fiction. This is the new reality of space exploration, a field that has transformed from a quest for knowledge into a direct pipeline for revolutionary change. The discoveries being made right now, by telescopes peering to the edge of time and by probes touching alien worlds, are not just expanding our understanding of the universe. They are sending back echoes that are beginning to fundamentally reshape life right here on Earth. Today, we are embarking on a journey to count down 30 of the most profound space discoveries that hold the genuine potential to alter our future. We are not just talking about fascinating curiosities for astronomers. These are tangible, groundbreaking revelations that are already sending ripples through the fields of medicine, technology, energy production, and agriculture. They challenge our most basic assumptions about our place in the cosmos and offer solutions to problems that have plagued humanity for generations. This is about finding new elements in the hearts of dead stars that could lead to stronger materials, or studying the harsh environment of Mars to develop new ways to grow food in a changing climate. It is about looking at the way planets form to understand the very origins of life itself. Each discovery is a piece of a grander puzzle, and when assembled, this new picture of the universe doesn't just show us what's out there, it shows us a new vision of what is possible here at home. So prepare to have your perspective shifted. We are going to travel from the silent, frozen oceans of distant moons to the violent, energetic hearts of distant galaxies, uncovering secrets that carry the power to redefine our world. This is a story of human ingenuity reaching out into the void and finding answers we didn't even know we were looking for. It is a testament to our relentless curiosity, a quality that has always been our greatest asset. As we explore these 30 incredible findings, you will see that the line between space science and everyday life is blurring, and the future is arriving faster than we ever thought possible. Let's begin our countdown. And so, our countdown begins not with a distant star or an exotic galaxy, but with our own familiar celestial companion, the Moon. For centuries, we gazed upon its dusty, gray surface and saw a barren, desolate world. But recent discoveries have completely rewritten that story, revealing a secret the Moon has been hiding in its darkest, coldest corners. Our first groundbreaking discovery is the definitive confirmation of water ice, locked away in the permanently shadowed craters at the lunar poles. These are deep pits where sunlight has not reached for billions of years, creating some of the coldest places in our entire solar system. Perfect deep freezes for preserving water in the form of ice. This isn't just a scientific curiosity. It is a game changer for the future of humanity in space. Think of water not just as something to drink, but as a fundamental resource that can be broken down into its core components: hydrogen and oxygen. Oxygen, of course, is essential for astronauts to breathe. But when you combine hydrogen and oxygen, you create an incredibly powerful rocket fuel. This simple fact transforms the Moon from a mere destination into something far more valuable: a cosmic gas station. The implications of this are staggering. Launching anything from Earth's surface requires an enormous amount of energy to escape our planet's powerful gravity. But the Moon's gravity is only 1/6 of Earth's, meaning it takes far less fuel to launch from there. If we can extract water ice from the lunar soil and process it into rocket fuel, Spacecraft could refuel on the Moon before venturing out to Mars, the asteroids, or beyond. This completely alters the economics of space exploration. Instead of carrying all the fuel for a round trip from Earth, a tremendously heavy and expensive endeavor, we can essentially produce it off-world. This concept, known as in situ resource utilization, turns a dead rock into a vibrant hub of activity. Missions like NASA LCROSS, which deliberately crashed a spacecraft into a shadowed crater to analyze the resulting plume, and India's Chandrayaan-1, which used instruments to map the presence of water molecules, provided the hard evidence that made this vision a tangible reality. This discovery paves the way for a new, off-world economy, one based not on mining for precious metals alone, but on harvesting the most precious resource of all, the very means of survival and propulsion. The Moon is no longer just a symbol in the sky. It has become the first stepping stone in our journey to the stars. Moving from the Moon's frozen water to the red sands of Mars, we find our next discovery, one that strikes at the very heart of a question humanity has asked for generations: are we alone? Discovery number 2 takes us to the work of robotic geologists like the Curiosity and Perseverance rovers, which have made the monumental find of complex organic molecules embedded within ancient Martian rocks and soil. Now, it's crucial to clarify what organic means in this scientific context. It doesn't automatically mean alive or even from life. Instead, these are carbon-based compounds, the fundamental chemical scaffolding that life as we know it is built upon. Think of them as the Lego bricks scattered on a cosmic playroom floor. Finding them on Mars is like finding a box of unassembled Lego bricks. It doesn't prove a castle was ever built there, but it confirms that all the necessary pieces were present and available. The significance of this cannot be overstated. For decades, Mars was considered a sterile, oxidizing environment where such delicate carbon compounds would be quickly destroyed. The rovers, by drilling into billion-year-old rocks in what were once ancient lakebeds, have shattered that assumption. They've sniffed out molecules like thiophenes and aromatic hydrocarbons, which are sturdy, ring-shaped structures that can persist for eons. This discovery tells us that the basic chemical prerequisites for life existed on Mars when it was a warmer, wetter world, much like early Earth. It transforms Mars from a simple dead rock into a planet that was once chemically ripe for life to potentially emerge. The implications spiral out from this point. The most immediate and thrilling question is whether this organic material is simply the leftover chemical graffiti of non-biological processes, or if it is the fossilized signature of ancient Martian microbes. The Perseverance rover is actively addressing this by carefully sealing dozens of core samples, which a future mission will eventually bring back to Earth for analysis in labs far more sophisticated than any that can fit on a rover. But the value of this discovery extends far beyond the hunt for little green men. By studying these preserved organic molecules on Mars, we are essentially looking at a snapshot of a planetary experiment that ran a different course than Earth's. Our own planet's ancient biological history has been almost entirely overwritten by plate tectonics and a vibrant biosphere. Mars, however, presents a pristine, frozen record of its early chemistry. Analyzing these compounds can teach us universal rules about how life can get started anywhere. It helps us understand the pathways from simple chemistry to complex biology, potentially rewriting our textbooks on the origin of life itself. This research doesn't just inform us about Mars. It refines our search for life on the icy moons of Jupiter and Saturn, and on distant exoplanets. It gives us a new chemical vocabulary for recognizing the signatures of life, a vocabulary we are only just beginning to learn. The discovery of organics on Mars is a quiet, yet profound, clue in the universe's greatest detective story, suggesting that the ingredients for life are a common cosmic currency, waiting for the right conditions to assemble into something truly miraculous. But now, Let's journey far beyond our solar system to a discovery that redefines the very idea of a planetary neighborhood. At a distance of about 40 light-years, a cosmic distance that is staggering to contemplate yet practically next door in the grand scale of our galaxy, lies an astronomical treasure trove known as the TRAPPIST-1 system. What makes this system so extraordinary isn't just the number of planets, it has 7, but the fact that every single one of them is roughly the size of Earth. This is a completely different architecture from our own solar system. Instead of a few small rocky worlds close to the Sun and gas giants further out, the TRAPPIST-1 system is a compact family of terrestrial planets, all orbiting incredibly close to their star. If you were to stand on the surface of one of these worlds, the other planets would appear in your sky as large as our Moon, or even larger, creating a breathtaking celestial panorama. The star at the center of this system is a cool red dwarf, much smaller and dimmer than our Sun. Because of this, the habitable zone, that narrow Goldilocks region where temperatures are just right for liquid water to potentially exist on a planet's surface, is also much closer in. And remarkably, not just one, but 3 of these 7 Earth-sized worlds orbit within this habitable zone. This single discovery exponentially increased the number of known planets with the right orbital conditions for life. The potential for these worlds to host liquid water is immense, but the presence of water depends on another critical factor: an atmosphere. A planet could be in the perfect spot, but without a substantial atmosphere to trap heat and maintain pressure, any water would either freeze solid or boil away into space. The incredible news is that initial studies with telescopes like the Hubble, and more recently, the James Webb Space Telescope, suggest that at least some of these planets do indeed hold onto atmospheres. The next step is to analyze the chemical composition of those atmospheres, searching for the telltale biosignatures, gases like oxygen, methane, or ozone that, in certain combinations, could be a strong indication of biological activity. Studying the TRAPPIST-1 system is like being given a fully equipped laboratory for understanding how planets form and evolve. Its compact nature means the planets likely influence each other gravitationally, which could affect their climates and even their potential to support life. By comparing these 7 siblings, astronomers can investigate why some planets develop thick atmospheres while others lose them, why some might become oceanic worlds and others dry deserts. This system provides a controlled experiment on a cosmic scale, offering insights that we simply cannot gain from our own, more spread-out solar system. The discovery of TRAPPIST-1 shattered the previous paradigm of what a planetary system could look like. It demonstrated that packed systems of Earth-sized worlds are not rare flukes, but could be common around the vast population of red dwarf stars in our galaxy. This fundamentally alters the equation in the search for life beyond Earth, suggesting that the cosmic real estate suitable for biology might be far more abundant than we ever dared to hope. While the TRAPPIST-1 system offers an incredible nearby example, it is merely one single day, a point in a revolution that has quietly unfolded over the past 2 decades. This brings us to our 4th discovery, a statistical revelation so profound it has permanently altered our cosmic self-image. Thanks to missions like NAS, a Kepler Space Telescope, and its successor, TESS, we have moved from wondering if other planets exist to confirming that they number in the thousands, with a significant fraction orbiting within what astronomers call the habitable zone. You might know this region by its more popular name, the Goldilocks zone. The concept is elegantly simple yet monumental in its implications. It describes the orbital distance from a star where the temperature is not too hot and not too cold, but just right for liquid water to potentially pool on a planet's surface. Why is water the magic ingredient? Because here on Earth, wherever we find liquid water, from scorching hydrothermal vents to frozen subterranean lakes, we find life. It is the universal solvent, the essential medium for the complex chemistry of biology as we understand it. The sheer abundance of these worlds is what makes this discovery truly transformative. Kepler, by staring relentlessly at a single patch of sky and monitoring the faint dimming of stars as planets passed in front of them, revealed that planets are not the exception but the rule. It demonstrated that most stars in our galaxy have at least one planet orbiting them. When you extrapolate those findings across the hundreds of billions of stars in the Milky Way, the numbers become staggering. Conservative estimates now suggest there could be tens of billions of Earth-sized planets residing in the habitable zones of their stars. Let that number sink in. We are no longer talking about a handful of possibilities. We are talking about a galaxy that could be filled with real estate that meets the basic conditions for habitability. This statistical leap fundamentally challenges the long-held notion of Earth's rarity. For centuries, we could look up and reasonably assume our world was a singular oasis. Now, the data suggests we live in a cosmic archipelago, a galaxy teeming with potential islands of life. This shift from philosophy to statistics has had a concrete and exhilarating impact on the science of astrobiology. The question is no longer, are there other habitable worlds? But rather, what kind of life might they host? The discovery of these Goldilocks planets has provided a tangible, prioritized target list for the next generation of observatories, most notably the James Webb Space Telescope. Instead of scanning the sky blindly, astronomers can now point their powerful instruments at these specific, known worlds and analyze their atmospheres. They will look for the chemical fingerprints of life, or biosignatures. The most promising of these is the combination of oxygen and methane. On Earth, these two gases react with each other and would quickly disappear from the atmosphere if they weren't continuously replenished by biological processes, primarily by plants and microbes. Detecting a similar unstable mixture in the atmosphere of a distant exoplanet would be the strongest hint yet that we are not alone. But the concept of the habitable zone itself is also evolving, adding fascinating layers of complexity to our search. We are learning that a planet's position relative to its star is just the beginning of the story. A world's long-term habitability depends on a host of other factors. Does it have a protective magnetic field to shield it from deadly stellar radiation? Is it a geologically active planet, with volcanoes and plate tectonics that help regulate its atmosphere and climate over billions of years? What is the nature of its host star? Many of these planets orbit volatile red dwarfs, which are prone to intense flares that could strip away atmospheres and sterilize surfaces. This has led scientists to consider the idea of an extended habitable zone, which might include icy moons like Europa or Enceladus in our own solar system. These worlds are far from the sun's warmth, but they are kept liquid internally by the gravitational tug of war with their giant parent planets, suggesting that life could thrive in subterranean oceans completely disconnected from stellar heat. This expanded view means the number of potential abodes for life is even greater than we first imagined. The discovery of thousands of worlds in the Goldilocks zone has not given us a simple answer, but it has given us a universe rich with possibility, transforming our quest from a hopeful gaze into a strategic, data-driven investigation of the cosmos. This discovery of countless Goldilocks worlds makes the universe feel both vast and intimately connected, a place where the building blocks of life might be commonplace. But what if we didn't have to wait for a telescope to analyze the light from a distant star? What if pieces of other planetary systems were already, right now, sailing through our own cosmic backyard? This brings us to a moment in 2017 that sent a jolt of excitement through the astronomical community with the detection of our fifth landmark discovery, the first known interstellar object named Oumuamua. In Hawaiian, the name means a messenger from afar arriving first, and it was a perfect description. For the first time in history, we had direct, tangible evidence of an object that had formed around another star, an alien visitor passing through our solar system. The initial observations revealed a string of bizarre properties that made Oumuamua utterly unique. First was its shape. While most asteroids and comets in our solar system are roughly spherical or lumpy potatoes, Oumuamua appeared to be highly elongated, shaped like a cigar or a pancake, tumbling end over end through space. This was strange enough, but then came the real head-scratcher, its acceleration. As it traveled away from the Sun, its path couldn't be explained by gravity alone. Something was giving it an extra push, a non-gravitational acceleration. With comets, this is usually easy to explain. Heat from the Sun vaporizes ice on the surface, creating jets of gas that act like tiny thrusters. The puzzling thing about Oumuamua was that telescopes detected no visible coma, the cloud of gas and dust that typically surrounds a comet's nucleus, and no tail. It was dark, reddish, and seemingly inert, like a bare rock. Yet it was accelerating as if it had a hidden engine. This combination of mysteries naturally sparked a wide range of theories. The mainstream scientific explanation suggests Oumuamua could have been a very unusual type of comet, one composed of very pure water ice or other ices that vaporized without releasing much visible dust, or perhaps a chunk of solid hydrogen or nitrogen ice that sublimated away invisibly. Another compelling idea is that it was a fragment of a Pluto-like planet from another system, a shard of nitrogen ice sheared off in a cosmic collision. The lack of outgassing dust could be explained if the object had been baked by cosmic rays over its long journey, creating a thick, carbon-rich crust that sealed in any volatile materials, with the gas escaping through unseen cracks. Then, of course, there were more speculative ideas, including the fascinating, though highly unlikely, possibility that it was a piece of alien technology, like a light sail. While most scientists lean towards natural explanations, the very fact that such a debate was possible underscores just how peculiar this visitor was. Beyond the mystery of its identity, the truly profound implication of Oumuamua's visit is what it tells us about the traffic of interstellar material. Its detection implies that there are countless such objects wandering the void between stars. Before 2017, this was just a theory. Now we have proof. Our solar system isn't a closed ecosystem. It is constantly being traversed by fragments from other star systems, offering us free, delivered samples of the chemical and geological processes at work around distant suns. We just needed the technology to spot them. Following Oumuamua, a second interstellar object, Comet Borisov, was discovered in 2019. Unlike Oumuamua, Borisov looked and behaved much like a regular comet, complete with a visible coma and tail, demonstrating that interstellar visitors can be both bizarrely unique and comfortably familiar. This has opened an entirely new field of astronomy dedicated to studying these interstellar interlopers. Future observatories like the Vera C. Rubin Observatory are expected to find many more each year, allowing us to build a catalog of what other planetary systems are made of. Each one is a time capsule, a messenger carrying the untold stories of its birth star, and they are arriving on our doorstep without us ever having to launch a probe. The detection of gravitational waves represents a revolution not just in what we can observe, but in how we observe the universe itself. For centuries, astronomy has been entirely dependent on light, on the photons that travel across the cosmos to reach our eyes and our telescopes. But light can be blocked, absorbed, or distorted. Gravitational waves are something entirely different. They are ripples in the very fabric of space-time, predicted by Albert Einstein over a century ago as a consequence of his general theory of relativity. Imagine space-time as a vast, flexible trampoline. When massive objects move or accelerate, particularly in violent events, they create waves that propagate outward at the speed of light, stretching and squeezing space itself as they pass. For decades, this was considered an untestable prediction. The waves were thought to be so incredibly faint by the time they reached Earth that detecting them seemed nearly impossible. That all changed in 2015 with the Twin Laser Interferometer Gravitational Wave Observatory, or LIGO, facilities in the United States. These are not traditional telescopes, but perhaps the most precise measuring instruments ever built. Each L-shaped observatory has arms 4 kilometers long. A laser beam is split and sent down each arm, bouncing off mirrors to travel back and recombine. In perfectly calm spacetime, the light waves cancel each other out. But when a gravitational wave passes through Earth, it minutely changes the length of one arm relative to the other, by a distance thousands of times smaller than the nucleus of an atom. This tiny change alters the laser light pattern, creating a signal. The first signal ever detected was the unmistakable chirp of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging in a cataclysmic event that occurred over 1 billion light-years away. This was not a flash of light or a burst of radiation. It was the literal sound of spacetime ringing from the impact. This discovery confirmed Einstein's last major unverified prediction and inaugurated an entirely new field, gravitational wave astronomy. It's like giving humanity a new sense. Before this, we could only see the universe. Now, we can literally hear it. This is profound because some of the most energetic and mysterious events in the cosmos are completely dark to traditional telescopes. Black holes, by their very definition, emit no light. But when they merge, they send out a thunderous announcement in the form of gravitational waves, allowing us to study these invisible monsters directly for the first time. Each collision provides a wealth of information, allowing scientists to weigh the black holes, measure their spins, and test the laws of gravity under the most extreme conditions imaginable. Since that first detection, LIGO and its European partner, Virgo, have heard the mergers of many more black holes, and even the spectacular collision of two neutron stars, an event that was also observed by telescopes across the electromagnetic spectrum, creating a multi-messenger picture of a cosmic event that was previously only theoretical. The implications for fundamental physics are staggering. By studying these waves, we are probing the nature of gravity itself, the least understood of the 4 fundamental forces. We are testing whether Einstein's theory holds true in the intense gravity of a black hole merger, or if subtle deviations might point toward new physics, perhaps even clues that could help unite general relativity with quantum mechanics. Furthermore, gravitational waves offer a pristine record of these violent events. Unlike light, which can be scattered and altered by dust and gas on its long journey, gravitational waves pass through matter almost completely unaffected. They bring us a clean, undistorted signal from the heart of the cataclysm. As our detectors become more sensitive, we will be able to hear the ripples from even more exotic phenomena, like the cosmic strings left over from the Big Bang or the background hum from supermassive black holes merging at the centers of galaxies. This new sense of hearing is allowing us to listen to the hidden symphony of the universe, a symphony that has been playing all along, but that we are only now, for the very first time, able to perceive. From the silent ripples of gravitational waves, we now turn to the oldest light in existence, a faint whisper of heat that fills every corner of the cosmos. Our 7th discovery is the cosmic microwave background radiation, often called the CMB. This is not the light from the first stars or the earliest galaxies. This is something far more primordial. It is the remnant glow from the birth of the universe itself, the afterglow of the Big Bang. To understand its significance, we need to wind the cosmic clock back nearly 13.8 billion years. In the very first moments, the universe was an unimaginably hot, dense soup of fundamental particles and energy. It was so dense that light could not travel freely. It was constantly scattered, trapped in a brilliant, opaque fog. For hundreds of thousands of years, this searing plasma filled all of space. Then, about 380,000 years after the beginning, a monumental transition occurred. The expanding universe had cooled enough for electrons to combine with protons to form the first neutral atoms, mostly hydrogen. This event, known as recombination, suddenly cleared the fog. For the first time, photons of light could travel across the cosmos unimpeded. The light that was released at that exact moment is what we detect today as the cosmic microwave background. Think of it as the universe's baby picture, a snapshot of what it looked like at that tender age of 380,000 years. Of course, that light has been traveling for almost 14 billion years, and the expansion of the universe has stretched its wavelengths enormously, shifting it from visible light all the way down to the microwave part of the spectrum. This is why we perceive it not as a blinding flash, but as a uniform, cold glow permeating space, with a temperature of just about 2.7 degrees above absolute zero. The initial discovery of this background radiation in the 1960s was almost accidental. Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs, were troubleshooting a persistent, annoying hiss in their sensitive horn antenna. They tried everything to eliminate it, even cleaning out pigeon droppings, but the faint, uniform static remained, coming from every direction with no variation. They had inadvertently stumbled upon the cooled remnant of the universe's fiery birth, a discovery that earned them the Nobel Prize and provided the first direct, smoking gun evidence for the Big Bang Theory, triumphing over competing models. But the story doesn't end there. The true revolution came decades later with satellites specifically designed to study this ancient light with exquisite precision, most notably the COBE, WMAP, and Planck missions. These observatories revealed that the CMB is not perfectly smooth. Embedded within its uniform glow are tiny, tiny variations in temperature, anisotropies that appear as a mottled pattern of slightly warmer and slightly cooler spots. These fluctuations are incredibly small, differing by only about 1 part in 100,000, but they are arguably the most important features in the entire cosmos. They represent the seeds of all cosmic structure. Those minute density variations, those slightly hotter, denser patches, were the gravitational anchors around which matter began to clump. Over billions of years, gravity amplified these tiny imperfections, pulling in more and more gas and dust, eventually forming the vast cosmic web of galaxies, galaxy clusters, and superclusters that we see today. Our own Milky Way galaxy and everything in it originated from one of those faint specks in the CMB. By meticulously mapping these patterns, cosmologists have been able to perform something like a cosmic ultrasound, determining the fundamental properties of the universe with breathtaking accuracy. The specific size and distribution of the fluctuations tell us the universe's age, 13.8 billion years. They reveal its geometry, confirming that on the largest scales, the universe is flat, meaning parallel lines will never meet, a critical finding for understanding its ultimate fate. Most astonishingly, the CMB data allows us to inventory the entire cosmos. It tells us that the ordinary matter that makes up stars, planets, and us constitutes less than 5% of the total content of the universe. About 27% is the mysterious dark matter, which provides the gravitational scaffolding for galaxies, and a whopping 68% is dark energy, the enigmatic force responsible for the accelerating expansion of the universe. The cosmic microwave background, this faint echo of creation, has provided us with the definitive recipe for the cosmos, a single data set that has shaped our modern understanding of where we came from and what the universe is ultimately made of. Building on the profound revelations from the cosmic microwave background, which gave us a detailed baby picture of the universe, we arrive at a discovery so unsettling that it forced cosmologists to rewrite the final chapter of cosmic history before they had even finished reading the first. This is discovery number 8, the shocking revelation that the expansion of the universe is not slowing down as everyone expected, but is in fact accelerating, flying apart at a faster and faster rate. For decades, the prevailing model was straightforward. After the initial fireball of the Big Bang, the universe had been coasting outward, its expansion gradually being braked by the relentless pull of gravity from all the matter contained within it. The central question for astronomers was simply whether there was enough matter to eventually halt the expansion and pull everything back together in a big crunch, or if the universe would just keep expanding forever, slowly cooling into a dark, quiet eternity. It was a cosmic tug-of-war between the momentum of the Big Bang and the steady grip of gravity. To settle this debate, two independent teams of scientists in the late 1990s embarked on an ambitious project. They aimed to measure the expansion rate over cosmic time by observing a specific kind of stellar explosion, a Type 1a supernova. These explosions occur in binary star systems and have a very predictable peak brightness, making them what astronomers call standard candles. By measuring how bright these supernovae appear from Earth, scientists can calculate their precise distance. Furthermore, by analyzing the light from these incredibly distant explosions, which has been traveling for billions of years, they can determine how much the universe has stretched since the light was emitted. The teams expected to see that the more distant supernova, those that exploded longer ago, showed signs of a universe expanding faster in the past, evidence of the expected deceleration. Instead, they found the exact opposite. The faraway supernovae were fainter than they should have been, meaning they were farther away than predicted. The only possible explanation was that the expansion of the universe was slower in the past and has been speeding up over billions of years. It was as if you threw a ball into the air, and instead of slowing down and falling back to Earth, it shot away from you faster and faster into the sky. This discovery was so counterintuitive and revolutionary that it earned the team leaders the Nobel Prize in Physics in 2011. The force responsible for this bizarre acceleration was given a name that perfectly captures our ignorance: dark energy. We cannot see it, we cannot detect it directly, and we have no idea what it is. Yet, based on its profound effect on the cosmos, we can calculate that it makes up about 68% of the total mass energy content of the universe. Think about that for a moment. The stars, galaxies, planets, and every single thing we can see and touch with our most powerful instruments accounts for less than 5% of reality. Dark matter, another mystery, makes up about 27%. But dark energy, this enigmatic repulsive force, is the dominant component of the cosmos. Its discovery humbled us, revealing that we understand the nature of barely a 20th of the universe we call home. The implications of this accelerating expansion are monumental, stretching all the way to the ultimate fate of everything. The most widely accepted model suggests that dark energy is a property of space itself. As the universe expands, more space comes into existence, which in turn creates more dark energy, leading to a runaway effect. If this continues, the most likely outcome is a scenario known as the heat death, or Big Freeze. In this distant future, billions upon billions of years from now, the acceleration would become so dominant that the universe outside our local group of galaxies would effectively disappear. The light from those distant galaxies would be redshifted so severely that their wavelengths would be stretched beyond detection. The cosmos would become a vast, ever-cooling emptiness, with isolated islands of stars growing dark one by one. It would be a quiet, desolate, and incredibly lonely end. But there is another, even more dramatic possibility known as the Big Rip. This scenario depends on the exact strength and nature of dark energy. If the repulsive force grows stronger over time, it could eventually overcome all other forces, not just on a cosmic scale but on a microscopic one. First, galaxy clusters would be torn apart. Then, individual galaxies. As the acceleration intensifies, the gravitational hold of stars and planets would be broken. In the final moments, even atoms themselves would be ripped apart, with the repulsive force overcoming the nuclear forces that bind protons and neutrons together. The entire fabric of reality would be shredded in a final, violent instant. While the Big Freeze is currently the favored model, the very existence of dark energy means that these cosmic destinies are now real possibilities we must contend with. The discovery of dark energy transformed cosmology from a science that could explain the past into one that is now forced to grapple with a deeply strange and unpredictable future, all governed by a force that remains one of the greatest mysteries in all of science. While dark energy governs the vast, empty stretches of the cosmos, pushing galaxies apart, there is another, equally mysterious force at work on a slightly smaller scale, holding the universe together. This brings us to discovery number 9, the enigmatic substance known as dark matter. If dark energy is the ghostly fuel of cosmic acceleration, then dark matter is the invisible skeleton upon which the visible universe is built. We cannot see it, touch it, or detect it with any of our instruments in a conventional way because it does not interact with light at all. It neither emits, absorbs, nor reflects electromagnetic radiation. It is completely transparent, and yet, we know with absolute certainty that it exists because of the profound gravitational footprint it leaves on everything we can see. The first compelling evidence for dark matter emerged from the study of how galaxies spin. In the 1930s, astronomer Fritz Zwicky was observing the Coma cluster, a massive group of galaxies, and noticed something bizarre. The individual galaxies within the cluster were moving so quickly that the collective gravity of all the visible stars and gas should not have been nearly strong enough to hold the cluster together. The galaxies should have flown apart long ago. Zwicky proposed the existence of some kind of Dunkel Materie, or dark matter, providing the extra gravitational glue. Decades later, in the 1970s, Vera Rubin provided the definitive proof by meticulously measuring the rotation speeds of stars within individual spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly than stars closer to the center, just as Pluto orbits the Sun more slowly than Mercury. But Rubin's data showed the opposite. Stars at the edge of spiral galaxies orbit just as fast as those near the center. The only plausible explanation is that each galaxy is embedded within a vast, spherical halo of some invisible material, a halo that extends far beyond the visible edge of the galaxy. This dark matter halo provides the extra gravitational pull to keep those high-speed outer stars from being flung off into intergalactic space. Another powerful line of evidence comes from a phenomenon predicted by Einstein called gravitational lensing. The immense gravity of a massive object, like a galaxy cluster, warps the fabric of spacetime around it, acting like a giant cosmic lens. This distortion bends the path of light coming from galaxies that lie far behind the cluster, creating stretched, magnified, and sometimes multiple images of those background galaxies. By carefully mapping the distortion, astronomers can calculate the total mass of the foreground cluster required to create such a lensing effect. Time and again, the result is the same. The mass required is 5 to 10 times greater than the mass of all the visible stars, gas, and dust combined. The stunning images from the Hubble Space Telescope are filled with these giant cosmic lenses, and each one silently testifies to the overwhelming presence of this unseen mass. It's as if we are looking at a city at night, seeing only the pinpricks of light from street lamps and windows, but through the lens of gravity, we can map the outline of the entire, darkened metropolis that those lights belong to. So what could this invisible substance possibly be? The leading candidate is a class of hypothetical particles known as WIMP, or weakly interacting massive particles. These would be particles that do not participate in the electromagnetic or strong nuclear forces, only interacting with normal matter through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Dozens of sophisticated experiments are underway deep underground, in abandoned mines and tunnels, where scientists hope to catch the incredibly rare flash of energy that would occur if a WIMP particle ever collided with an atom in a super-sensitive detector. Other possibilities include actions, which are extremely light particles, or even MACHO, which stands for emissive compact halo objects. Things like black holes, neutron stars, or rogue planets that are simply too dark to see. However, detailed surveys have ruled out MACHO as being the primary component of dark matter. There just aren't enough of them to account for the gravitational effects we observe. Solving the mystery of dark matter is arguably the greatest outstanding challenge in modern physics. Its discovery would not just fill a gap in our knowledge, it would represent a monumental leap forward, likely pointing to entirely new laws of nature beyond the standard model of particle physics, which has been spectacularly successful at explaining the world of visible matter, but has no suitable candidate for dark matter. The technological implications are equally profound. Every time humanity has unlocked a fundamental force of nature, it has led to a technological revolution. Understanding electromagnetism gave us the electric grid, radio, and computers. Harnessing the weak nuclear force is the goal of fusion energy. If we could ever understand the nature of dark matter well enough to manipulate it, the possibilities are mind-boggling. It could open up avenues for propulsion systems that manipulate gravity itself, or provide insights into entirely new states of matter. But perhaps the most profound impact would be philosophical. To finally identify the substance that makes up 27% of the cosmos, the unseen foundation of every galaxy, would complete our cosmic inventory and finally allow us to see the full picture of the universe we inhabit, a picture that, for now, remains largely in the dark. After exploring the vast, invisible realms of dark matter and dark energy, we come to a discovery that grounds these cosmic mysteries in a singular, terrifyingly tangible object. At the very heart of nearly every large galaxy, including our own Milky Way, lies a gravitational monster of almost incomprehensible scale, a supermassive black hole. These are not the stellar mass black holes formed from the collapse of a single giant star. These are behemoths, containing the mass of millions or even billions of suns squeezed into a region of space no larger than our solar system. For a long time, their existence was inferred rather than seen. We observed stars at the galactic center whipping around an invisible point at speeds of thousands of kilometers per second, their frenzied orbits betraying the presence of an immense, unseen mass. But in 2019, humanity achieved the seemingly impossible. We took a picture of one. The Event Horizon Telescope project did not use a single telescope. Instead, it linked observatories across the globe, from the high deserts of Chile to the volcanic peaks of Hawaii, creating a virtual telescope the size of Earth itself. This global effort was aimed at two targets: the black hole at the center of our galaxy, known as Sagittarius A star, and the even larger one at the heart of the distant galaxy Messier 87. The resulting image of the M87 black hole is iconic. It shows a brilliant, fiery ring of light, a whirlpool of superheated gas swirling at near light speeds, encircling a perfect circle of profound darkness, the shadow of the black hole's event horizon. This is the point of no return, the boundary beyond which not even light can escape the gravitational pull. That dark silhouette, set against the glowing accretion disk, provided the first direct visual evidence of a black hole's existence, and matched the predictions of Einstein's theory of relativity with stunning accuracy. The presence of these supermassive black holes is not a mere cosmic curiosity. It is a fundamental driver of galactic evolution. We now understand that galaxies and their central black holes grow up together in a complex, co-evolutionary dance. The black hole feeds on the gas, dust, and even stars that fall into its grasp. But this feeding process is not a silent consumption. As matter spirals inward, friction and magnetic fields heat it to millions of degrees, causing it to emit tremendous amounts of radiation. In its most active phase, a black hole becomes a quasar, shining with the brightness of 1 trillion stars, outshining its entire host galaxy. This outpouring of energy acts as a cosmic feedback mechanism. The intense radiation and powerful jets of particles that can erupt from the poles of the black hole blow away surrounding gas, effectively shutting off the raw material needed for both further black hole growth and the formation of new stars. This process regulates the size of the galaxy, preventing it from growing too large. It's a remarkable concept. The black hole, by its very act of violent consumption, sets a limit on the growth of its own home. This explains the surprising correlation astronomers have found between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. They are not independent entities. One has fundamentally shaped the other over billions of years. Studying these extreme environments is like conducting a natural experiment in physics under conditions we could never hope to recreate in a laboratory. The region near the event horizon is where gravity is pushed to its absolute limit, warping spacetime to an extreme degree. By observing how light and matter behave in this zone, we are conducting the most stringent tests ever of Einstein's general theory of relativity. So far, the theory has held up magnificently, but many physicists believe that at the very threshold of a black hole, where gravity becomes infinitely strong, we might finally see cracks in the theory, clues that point toward a deeper understanding that unites gravity with quantum mechanics. Furthermore, the study of supermassive black holes is intimately linked to the mysteries we've already discussed. They are thought to play a key role in the distribution of dark matter, their immense gravity potentially pulling the invisible substance into especially dense halos. They may even influence the large-scale structure of the universe, as the colossal jets from active galaxies can heat the intergalactic gas that sits between galaxy clusters, affecting where and how new galaxies can form. The discovery that these colossal engines reside at the center of galaxies has transformed them from science fiction nightmares into central characters in the story of the cosmos, proving that even the most destructive forces in the universe can also be creative, shaping the grand architecture of everything we see. From the destructive power of supermassive black holes, we turn to a celestial phenomenon that represents a far more gentle and beautiful cosmic finale, one that is intimately connected to our own existence. Discovery number 11 reveals the profound importance of planetary nebulae. At first glance, these objects are among the most stunning sights in the universe, appearing through telescopes as delicate, glowing shells of gas, often with intricate, symmetrical shapes like the famous Ring Nebula. For a long time, their name was a misnomer, given by early astronomers who thought their round shapes resembled the disks of planets like Uranus. We now know they have nothing to do with planets. Instead, a planetary nebula is the final, fleeting breath of a dying star similar in size to our own Sun. This beautiful death is the culmination of a star's life cycle. For billions of years, a star like our Sun fuses hydrogen into helium in its core, producing the energy that makes it shine. Eventually, the hydrogen fuel in the core runs out. The star then undergoes a dramatic transformation, swelling into a red giant as it begins fusing helium into carbon and oxygen in a shell around its core. This phase is unstable. The star pulsates, violently expelling its outer layers into space in a series of gentle, cosmic puffs. The hot, exposed core of the star, now called a white dwarf, is left behind. This tiny, Earth-sized remnant is incredibly hot, and its intense ultraviolet radiation causes the expanding shell of ejected gas to fluoresce, much like the gas in a neon sign. The nebula glows for only a brief period, perhaps 10,000 to 20,000 years, a mere blink in cosmic time, before it dissipates and fades into the interstellar medium. But it is in this act of dissipation that the true, lasting significance of planetary nebulae is found. They are not merely a pretty light show. They are fundamental agents of cosmic recycling. During its life, a star acts as a giant nuclear fusion furnace, creating elements heavier than the hydrogen and helium from which it formed. The red giant phase is particularly crucial because it is where significant amounts of carbon are forged. When the star sheds its outer layers to form a planetary nebula, it is ejecting this newly created, enriched material back into space. This stellar wind is laden with life-essential elements like carbon, the backbone of all organic chemistry, along with oxygen and nitrogen. These elements are scattered across the galaxy, mixing with clouds of primordial hydrogen and helium. This ejected material becomes the raw ingredients for the next generation of stars, planets, and ultimately, life. Our own solar system formed about 4.5 billion years ago from a cloud of gas and dust that had been enriched by the deaths of countless previous stars. Every atom of carbon in every molecule of your DNA, every atom of oxygen you just breathed in, and every atom of nitrogen in the air around you was once forged in the heart of a long-dead star, and then cast out into the galaxy by an event just like the formation of a planetary nebula. We are not just inhabitants of the universe in a passive sense. We are literally made of stardust. The calcium in your bones, the iron in your blood that carries oxygen, these two were created in even more massive stellar explosions. Planetary nebulae represent the specific delivery mechanism for the lighter elements that are fundamental to life as we know it. This discovery transforms our perspective from one of mere observation to one of deep connection. When we gaze at the ethereal beauty of a planetary nebula, we are looking at our own cosmic ancestry, the very process that seeded the galaxy with the building blocks that would, billions of years later, allow for planets like Earth and life like us to emerge. This protective bubble, known as the heliosphere, is our solar system's first line of defense against the harsh environment of interstellar space. It is not an empty void we pass through, but a dynamic structure created by the sun itself. Our star is constantly emitting a supersonic flow of charged particles, a stream of protons and electrons known as the solar wind. This wind races outward in all directions, pushing against the thin gas and dust that fills the space between stars. The heliosphere is the immense, teardrop-shaped cavity carved out by this relentless outward pressure, a cosmic fortress wall that extends far beyond the orbit of Pluto. For a long time, this was a theoretical concept, but its existence and shape have been confirmed by a fleet of robotic explorers, most famously the twin Voyager spacecraft. In 2012, Voyager 1 became the first human-made object to cross the boundary, known as the heliopause, and enter interstellar space, followed by its twin, Voyager 2, in 2018. These historic crossings provided the first direct measurements from the very edge of the Sun's influence, confirming that we live within a defined and active stellar envelope. The role of the heliosphere is absolutely critical for life on Earth. Beyond its boundary flows a relentless gale of galactic cosmic radiation. These are not mere particles from our Sun, but atomic nuclei accelerated to nearly the speed of light by distant supernova explosions and other violent cosmic events. They are incredibly energetic and can pierce through solid matter, posing a severe danger to unprotected life and sensitive electronics. The heliosphere acts as a massive magnetic shield, deflecting the vast majority of these harmful cosmic rays. Without this protective bubble, the flux of high-energy radiation reaching the inner solar system would be significantly higher. This would have profound implications for life, potentially leading to higher mutation rates in DNA and presenting a major challenge for the development and stability of complex organisms. It also affects our planet's climate. Some studies suggest a link between periods of a weaker solar wind, and thus a smaller heliosphere, and ice ages on Earth, as increased cosmic rays might seed more cloud formation. The heliosphere, therefore, is not just a fascinating astronomical feature. It is a fundamental contributor to the long-term stability and habitability of our world, quietly maintaining a safe environment for billions of years. Understanding the precise nature and stability of this shield is paramount, especially as we contemplate venturing beyond its protection. Missions like the Interstellar Boundary Explorer, or IBEX, have been dedicated to mapping the complex interactions at the edge of our solar system. IBEX doesn't travel to the boundary. Instead, it orbits Earth and detects energetic neutral atoms that are created when solar wind particles collide with particles from the interstellar medium. By collecting these atoms, IBEX can create a detailed map of the heliosphere's edge, much like a medical scan creates an image of the inside of a body. What it has revealed is astonishing. The boundary is not a smooth, simple bubble. It is a turbulent region of complex magnetic fields, shock waves, and a ribbon of intense energetic neutral atom emission that was completely unexpected and is still not fully understood. These findings show that our protective bubble is dynamic, breathing in and out as the sun goes through its 11-year cycle of activity, and buffeted by the pressure and magnetic orientation of the local interstellar cloud through which our solar system is moving. This has direct consequences for the future of human space exploration. An astronaut traveling to Mars is already exposed to higher levels of radiation than on Earth, but they are still within the relative safety of the heliosphere. A journey to another star, however, would require passing through the heliopause and spending centuries or millennia bathed in the full intensity of galactic cosmic rays. Developing shielding technology capable of protecting a crew for such a duration is one of the greatest engineering challenges we face. Furthermore, the discovery that the heliosphere is not static means we must also consider its history. As the Sun and the solar system orbit the galaxy, we pass through different regions of interstellar space, some denser than others. There is evidence to suggest that in the distant past, the heliosphere may have shrunk significantly when the Sun traveled through a dense cloud, potentially allowing more cosmic radiation to reach Earth and influence the course of evolution. Studying the heliosphere is thus about more than understanding our present neighborhood. It is about reading the historical climate record of our planet and forecasting the challenges that will define the next great age of human exploration into the galaxy. But perhaps the most mind-bending implication of all is that extremophiles don't just hint at life's potential elsewhere. They suggest a universe that might be actively sharing its biological riches. This leads us to the theory of panspermia, the idea that life itself could be a cosmic traveler, hitching rides on asteroids, comets, or even interstellar dust grains. For a long time, panspermia was considered a fringe idea, but the remarkable resilience of organisms like tardigrades has given it serious scientific credibility. The concept splits into two main ideas, lithopanspermia and radiopanspermia. Lithopanspermia is the more plausible scenario, where microbial life is shielded deep within the interior of a rock blasted off a planet's surface by a meteor impact. This rocky spaceship then journeys through space, potentially for millions of years, before crashing into another world. If the conditions on that new world are right, the microbial passengers could potentially revive and begin a new evolutionary chapter. The second idea, radiopanspermia, is far more speculative but even more astonishing. It proposes that microscopic life, like certain hardy bacteria or fungal spores, could survive the journey through space completely exposed, propelled by the faint pressure of starlight itself. The experiments on the International Space Station's exterior have shown that this isn't entirely impossible. While the vacuum and radiation of space are devastating, they are not always instantly 100% lethal to all organisms. A layer of dead cells on the outside of a clump could shield the living ones within, or the organisms might enter a state of suspended animation so deep that they can repair radiation damage upon encountering a suitable environment. If life can survive on the outside of a space station, could it survive a journey from Mars to Earth, or even between star systems? The distances are vaster and the timescales longer, making it incredibly challenging, but the fundamental principle is no longer pure science fiction. This dramatically changes our perspective on the origin of life on Earth. The classic question has always been, did life arise spontaneously here in a primordial soup, or could its seeds have arrived from elsewhere? The discovery of extremophiles doesn't answer that question, but it powerfully demonstrates that the second option is at least feasible. It means that life on our planet may not be a unique, isolated incident, but rather part of a much larger, interconnected biological network. A single inhabited world in a star system could, through asteroid impacts, potentially seed every other potentially habitable body in that system. If life began on a wet, early Mars before it dried up, it's conceivable that Martian microbes could have traveled to Earth on meteorites, making us all potentially descendants of Martians. This idea transforms our solar system from a collection of separate worlds into a single, interconnected biological zone. The ultimate implication of this is the concept of a galactic microbiome. If life can spread between planets within a system, and if rocky material can be ejected from one star system to another during close encounters, then the entire galaxy could be exchanging biological material over billions of years. Life may not have to start from scratch on every single habitable world. Instead, it might need to start just once, anywhere, and then spread, adapt, and evolve across the cosmos. This makes the universe feel far more biologically active and interconnected. The discovery that life on Earth possesses this innate, almost stubborn toughness to survive the void of space suggests that life is not a fragile flame, easily extinguished. It is more like a cosmic weed, tenacious and incredibly difficult to eradicate. This resilience greatly increases the probability that if we do find life elsewhere, it might share a common ancestry with life on Earth, or vice versa, suggesting that we are all citizens of a much larger, living galaxy. But while the idea of life spreading naturally between worlds is a grand cosmic possibility, humanity is also developing the tools to become an active participant in that process, not just as explorers but as prospectors. This brings us to a discovery that redefines resources, turning seemingly barren space rocks into the keystones of a future interplanetary economy. Discovery number 14 focuses on the immense potential of asteroid mining, a concept propelled by our growing knowledge of near-Earth objects. We have identified thousands of asteroids whose orbits bring them close to our planet, and detailed spectral analysis has revealed that these are not all just simple chunks of rock and ice. Among them are literal floating mountains of precious metals, containing concentrations of platinum, gold, cobalt, and iron that dwarf any deposits found on Earth. A single relatively small metallic asteroid, perhaps 500 meters across, could contain more platinum than has been mined in all of human history. The implications for our planet's industries are staggering. Many of these rare metals are absolutely essential for modern technology, from the catalytic converters that clean car exhaust to the circuitry in our smartphones and the powerful magnets in wind turbines and electric vehicles. Terrestrial mining for these materials is incredibly destructive, involving massive open-pit mines that consume vast amounts of water and energy, generate toxic waste, and disrupt local ecosystems. Accessing these resources from asteroids could fundamentally alter this equation. While the initial technological hurdles are immense, the long-term environmental benefits could be profound. It would allow us to source the critical materials for a green, high-tech civilization without further scarring the Earth's surface, effectively outsourcing the most damaging aspects of resource extraction to the void of space, where there is no ecosystem to harm. Perhaps even more valuable than the metals, however, is a far more humble resource: water. We've already discussed its presence on the Moon, but asteroids, particularly a class known as carbonaceous chondrites, are also rich in water ice and other volatiles. This transforms them from mere mineral deposits into cosmic gas stations and life support depots. The process, known as in situ resource utilization, would involve capturing a small water-rich asteroid or mining water from one, then using solar energy to split the water molecules into their component parts, liquid oxygen and liquid hydrogen. These are the fundamental ingredients of the most common and powerful chemical rocket fuels used today. The ability to produce fuel in space changes everything about the economics of exploration. Instead of launching all the propellant for a mission from Earth's deep gravity well at an astronomical cost, spacecraft could refuel in orbit or at a way station, such as a lunar base. This makes missions to Mars and beyond far more feasible and sustainable, enabling a true spacefaring infrastructure where vessels can travel much like ships at sea, refueling at ports along the way. This vision paves the way for a self-sustaining space-based economy. The materials mined from asteroids could be used not only for shipment back to Earth, but for construction in space itself. Imagine using the iron and nickel from an asteroid to build enormous solar power satellites that beam clean energy to Earth, or to construct habitats for long-term settlements on the Moon or Mars. The water could sustain those settlements, providing not just drinking water but oxygen to breathe and hydrogen for fuel. This creates a virtuous cycle where space resources enable further space development, which in turn unlocks more resources. The discovery that these valuable materials are within our reach has already spurred a nascent commercial space industry, with several companies actively developing the technology for prospecting and extraction. We are moving from seeing asteroids as celestial curiosities or potential threats to viewing them as strategic assets, the first stepping stones in humanity's journey to becoming a multi-planetary species. The wealth of the solar system is now within our sight, offering a path to a future where the Earth is preserved as a sanctuary, while the boundless resources of space fuel our continued growth and exploration. Moving beyond the promise of asteroid resources, we encounter a cosmic phenomenon that reminds us of our profound vulnerability to the star at the center of our own solar system. Our 15th discovery shifts the focus from opportunity to protection, as we delve into the volatile nature of solar activity and the emerging field of space weather. The Sun is not a constant, placid ball of light. It is a dynamic and occasionally violent sphere of magnetized plasma, with an activity cycle that peaks roughly every 11 years. During these active periods, the Sun can unleash two of the most powerful eruptions in the solar system: solar flares and coronal mass ejections, or CMES. A solar flare is a sudden, intense flash of radiation, a burst of light across the electromagnetic spectrum, that occurs when magnetic energy built up in the solar atmosphere is explosively released. While a flare travels at the speed of light, taking just over 8 minutes to reach Earth, a coronal mass ejection is something entirely different and far more physically substantial. A CME is a colossal bubble of billions of tons of solar plasma, threaded with powerful magnetic fields, that is hurled away from the Sun at speeds of millions of kilometers per hour. This is a solar hurricane of charged particles traveling through space, and when one is aimed directly at Earth, the consequences for our technology-dependent civilization can be severe. The real-world impact of a major CME striking Earth is not a hypothetical scenario from a science fiction film. We have a historical precedent that serves as a stark warning. In 1859, the Carrington event, named after the astronomer who observed the massive solar flare that accompanied it, unleashed a geomagnetic storm of unprecedented power. Telegraph systems, the cutting-edge technology of the era, failed spectacularly. Operators received severe electric shocks, telegraph paper caught fire, and some lines continued to operate even after being disconnected from their power supplies, running on currents induced in the wires by the storm itself. The aurora borealis, typically confined to polar regions, was seen as far south as Cuba and Hawaii, so brilliant that people could read newspapers by its light in the middle of the night. While this was a mesmerizing sight, a storm of similar magnitude striking Earth today would be catastrophic. Our modern world is woven together by a vastly more complex and sensitive technological web. The primary danger comes from the rapidly shifting magnetic fields of a geomagnetic storm, which can induce powerful electrical currents in long conductors on the ground, specifically in our continent spanning power grids. These geomagnetically induced currents, or GICS, can overload transformers, the massive and difficult-to-replace hearts of any electrical grid. Instead of simply blowing a fuse, these transformers can heat up internally, damaging their copper windings and melting their cores, leading to widespread, cascading blackouts that could last for months or even years while replacement parts, which are not kept in large inventory, are manufactured. The disruption would extend far beyond the loss of lights in our homes. Satellites orbiting Earth are on the front lines of such an event. The intense radiation from a solar storm can fry their sensitive electronics, degrade their solar panels, and cause permanent damage, knocking out global positioning systems, telecommunications, weather forecasting, and military surveillance networks. Airline flights, which rely on high-frequency radio communications over polar routes, would be grounded due to both communication blackouts and increased radiation exposure for passengers and crew. Banking and financial systems, which depend on precise timing from GPS satellites to timestamp transactions, would be thrown into chaos. In essence, a direct hit from a Carrington-level event could send the modern world back to a pre-industrial age in a matter of hours, triggering a global crisis of unprecedented scale. This sobering reality is what makes the discovery and continuous monitoring of space weather so critically urgent. Unlike terrestrial weather, which we can observe forming in our atmosphere, space weather originates 93 million miles away, giving us a very short window, anywhere from 18 hours to just a few days, to prepare once a CME is observed leaving the Sun. This is why a fleet of solar observatories like NAS, a Solar Dynamics Observatory, and the SOHO mission keeps a constant, vigilant watch on our star. Their data allows forecasters at space weather centers, like NOAA Space Weather Prediction Center, to issue alerts and warnings. Utilities can then take preventative measures, such as temporarily taking vulnerable transformers offline or adjusting grid loads to mitigate the impact of induced currents. The goal is not to stop the storm. That is impossible, but to manage its consequences and protect the foundational infrastructure of our society. As we become ever more reliant on technology, and as we venture further into space with crewed missions to the Moon and Mars, where astronauts would be outside the protective shield of Earth's magnetosphere, understanding and predicting the fury of our own star becomes not just a scientific curiosity, but a fundamental imperative for our civilization's security and its future among the stars. Yet, just as we learn to predict the storms from our own star, our exploration has also forced us to look inward and reconsider the very definitions we use to map our cosmic neighborhood. This brings us to discovery number 16, a finding that started with a single, distant world and ended up rewriting the textbooks on our solar system's structure. For generations, our model of the solar system was tidy and familiar: the Sun, 9 planets, and a sprinkling of asteroids. But in the early 1990s, astronomers began to detect faint, slow-moving objects beyond the orbit of Neptune. These weren't isolated oddities. They were the first glimpses of a vast, populous frontier now known as the Kuiper Belt. This region is a colossal disk of icy remnants, a cosmic junkyard stretching from Neptune's orbit out to a distance of about 8 billion kilometers from the Sun. It is our solar system's version of the asteroid belt, but it is far wider and contains hundreds of times more mass, populated by frozen bodies composed of water, methane, and ammonia ices mixed with rock. The most famous resident of this belt was, of course, Pluto. Discovered in 1930, it was celebrated as the 9th planet for over 75 years. But the discovery of the Kuiper belt itself cast Pluto in a new light. It was no longer a solitary wanderer at the edge of darkness. It was simply the largest and brightest known member of this immense swarm. The real paradigm shift came in 2005 with the discovery of Eris, a Kuiper belt object initially thought to be even larger than Pluto. This presented astronomers with a profound dilemma. If Pluto was a planet, then surely Eris, being its peer in size, must be one too. And if Eris was a planet, then what about the other sizable bodies being discovered in the Kuiper belt, like Makemake and Haumea? We were on the verge of having not 9 planets, but potentially dozens, even hundreds, as our telescopes improved. This wasn't a case of scientists taking away Pluto's status out of spite. It was a necessary step to create a clear, scientifically useful definition. The International Astronomical Union, the global body responsible for such classifications, was faced with a choice: either dramatically expand the list of planets indefinitely or refine the definition to reflect our new understanding. In 2006, they established 3 criteria for a planet. First, it must orbit the Sun. Second, it must have enough gravity to pull itself into a nearly round shape. And third, it must have cleared its orbital neighborhood of most other debris. This last point is the crucial one. A true planetary bully has, over billions of years, either consumed, flung away, or gravitationally dominated the other objects in its orbital path. Jupiter, for instance, has cleared its zone spectacularly. Pluto, however, shares its orbital space with thousands of other Kuiper belt objects. It is the king of its local swarm, but it has not cleared that swarm. Thus, Pluto, along with Eris and others, was reclassified as a dwarf planet. This decision was controversial for the public, but for scientists it was a milestone. It acknowledged that our solar system is not just a collection of 9 large worlds, but a complex system with a central planetary zone and a massive, dynamic outer belt, fundamentally changing our mental map of home. Beyond the classification debate, the true value of the Kuiper belt lies in its profound antiquity. The objects out there, known as Kuiper belt objects or KBOS, are cosmic time capsules. The inner solar system, with its rocky planets, has been dramatically altered by billions of years of geological activity, impacts, and the sun's heat. But in the deep freeze of the Kuiper belt, far from the sun's warming influence, these icy bodies have remained in a state of deep preservation since the solar system's birth over 4.5 billion years ago. They are the leftover building blocks from the planet-forming process, the pristine raw materials that never coalesced into a larger world. By studying them, we are effectively conducting an archaeological dig into the earliest moments of our solar system's formation. This is the primary reason NASA, a New Horizons mission, was so revolutionary. After its historic flyby of Pluto in 2015, which revealed a stunningly complex world with towering mountains of water ice and vast, smooth plains of frozen nitrogen, the spacecraft continued its journey deeper into the Kuiper belt. In 2019, it encountered a small, bizarre object named Arrokoth. Shaped like a flattened snowman, Arrokoth provided the clearest look yet at a primordial building block. Its 2 distinct lobes suggest it formed from a gentle collision of 2 separate objects in the ancient cloud of material that surrounded the young sun. Unlike planets which have been melted and reformed by violent impacts, Arrokoth appears largely undisturbed, a fossilized record of the gentle accretion process that built the first planetesimals. Analyzing its composition and structure helps us test theories of how planets themselves first began to clump together from dust. Each Kuiper belt object we study adds another piece to the puzzle, telling us about the chemical and physical conditions in the protoplanetary disk from which our entire system, and perhaps every system, is born. The redefinition of planets was not a demotion for Pluto, but a promotion for our understanding, revealing a solar system far richer, more dynamic, and more informative about our own origins than we ever imagined. But our journey through the outer solar system reveals that the ingredients for life are not confined to planets basking in the warmth of a star. Some of the most promising environments are hidden beneath the frozen, cracked surfaces of distant moons, a revelation that brings us to discovery number 17. Far from the Sun, in the deep chill of the Saturnian system, the small, icy moon Enceladus presents a world that has completely overturned our understanding of where life could thrive. For years, Enceladus was thought to be just another frozen ball, but the Cassini spacecraft unveiled a stunning secret. The moon is geologically active, with immense plumes of water vapor and ice crystals continuously erupting from a subsurface ocean, shooting hundreds of kilometers into space through giant fissures known as tiger stripes near its south pole. Cassini didn't just photograph these plumes, it famously flew directly through them, sampling their composition. The analysis was breathtaking. The plumes contained not just simple water ice, but a rich cocktail of salts, silica nanoparticles suggestive of hydrothermal activity on the seafloor, and a suite of organic molecules, the complex, carbon-bearing building blocks of life. Most intriguingly, the spacecraft detected significant amounts of methane gas. This discovery on Enceladus finds a powerful echo around Jupiter, where the moon Europa captivates scientists with its own secrets. Europa's surface is a labyrinth of cracks and ridges etched into a shell of water ice, a clear sign of a geologically active world. Beneath this icy crust, compelling evidence points to a global subsurface ocean containing more than twice the volume of all Earth's oceans combined. While we haven't yet sampled Europa's ocean directly, the Hubble Space Telescope has observed evidence of similar water vapor plumes erupting from its surface. The upcoming Europa Clipper mission is designed specifically to confirm these plumes and analyze their composition, and the expectation is high that it will find a chemical profile similar to Enceladus, including organic molecules and likely methane. The presence of methane on both these worlds is particularly tantalizing. On Earth, a substantial portion of atmospheric methane is produced by biological organisms, from microbes in wetlands to the digestive systems of cattle. While methane can also be produced through non-biological, geological processes called serpentinization, its detection in these watery environments immediately raises the possibility of a biological source. What truly elevates these moons from mere curiosities to top-tier candidates for life is the combination of three critical ingredients found in their hidden oceans. First and most obvious is the presence of liquid water in vast quantities. Second is the chemistry, confirmed by the detection of organic molecules, which provides the essential raw materials. But the third and perhaps most crucial ingredient is a source of energy. Life needs fuel, and on a world locked in ice, far from the warmth of the sun, photosynthesis is impossible. The energy for any potential ecosystem must come from within. This is where the concept of hydrothermal vents becomes paramount. The data from Enceladus strongly suggests that its rocky core is warm, heated by the intense gravitational flexing it experiences from Saturn's pull. This tidal heating likely drives hydrothermal systems on the ocean floor, similar to the black smokers found in the deepest, darkest parts of Earth's oceans. Around these vents on Earth, which spew mineral-rich, superheated water into the cold abyss, thriving communities of life exist completely independent of sunlight. The base of this food chain is microbes that perform chemosynthesis, using the chemical energy from the vent fluids to create organic matter. The detection of methane on Enceladus is consistent with such an environment, where microbes known as methanogens could theoretically consume hydrogen and carbon dioxide released from the rocks to produce methane as a waste product. This transforms our search for life from a planetary pursuit to an oceanic one. We are no longer just looking for Earth-like planets in habitable zones. We are looking for worlds with internal oceans, or water worlds, that maintain their liquid state through internal heat. Enceladus and Europa demonstrate that a star's habitable zone is not a fixed boundary, but can be extended dramatically by the tidal forces of a giant planet. This revelation massively increases the number of potential abodes for life in our galaxy alone. Imagine a dark, eternal ocean beneath miles of ice, illuminated not by sunlight but by the faint glow of hydrothermal vents. In that profound darkness, could there be ecosystems of microbial life, or perhaps even more complex organisms? The plumes erupting from these moons are like free samples, delivering the contents of their hidden oceans directly to our spacecraft. Future missions, like the Europa Clipper, will be equipped with advanced mass spectrometers to analyze the chemistry of these plumes in far greater detail, searching for patterns in the molecules that might hint at biological processes. The discovery of active, organic-rich oceans on Enceladus and Europa has fundamentally rewritten the rules of astrobiology, proving that life, if it exists, may not need a sun-drenched world, but could flourish in the lightless, abyssal depths of an alien sea, sustained by the quiet, internal heat of a small, icy moon. While the search for life leads us to the hidden oceans of icy moons, our journey through the cosmos also reveals forces operating on a scale so vast it challenges our very perception of motion. We now arrive at discovery number 18, a phenomenon that reminds us our galaxy is not a static island but a ship sailing on an immense cosmic current, pulled by a hidden destination. This is the mystery of the Great Attractor. For decades, astronomers have meticulously mapped the velocities of galaxies, and a peculiar pattern emerged. Our Milky Way, along with our entire local group of galaxies and the vast Virgo supercluster it belongs to, is not moving randomly through the universe. We are all streaming at a staggering velocity of over 2 million kilometers per hour toward a specific point in the sky, located in the general direction of the constellation Centaurus. Whatever is causing this collective motion has been given a name that captures both its power and our ignorance: the Great Attractor. The fundamental challenge in solving this mystery is one of cosmic perspective. The region of space where the Great Attractor is thought to lie happens to be directly behind the plane of our own Milky Way galaxy, an area astronomers call the zone of avoidance. From our vantage point within the galactic disk, this zone is heavily obscured by dense clouds of gas and dust, as well as the bright, crowded starlight of the Milky Way's central bulge. It is like trying to see a distant mountain range while standing in a dense, foggy forest. Our own surroundings completely block the view. For a long time, this region was a literal blind spot in our maps of the universe, a blank area on the celestial chart where our telescopes, particularly those working in visible light, could not penetrate. However, science has a way of peering through the fog. Astronomers turn to instruments that can see in wavelengths other than visible light, specifically radio and infrared radiation, which can pass through the interstellar dust that blocks our optical view. Pioneering surveys, most notably the H.I. Park's All-Sky Survey, used radio telescopes to map the distribution of neutral hydrogen gas in galaxies behind the zone of avoidance. What they revealed was astonishing. The Great Attractor is not a single, unimaginably massive object, but rather the gravitational core of a colossal supercluster of galaxies, now known as the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, is a filamentary web of galaxies spanning over 500 million light-years, and our own Milky Way is just a suburban speck on its outer fringes. The motion we observe is essentially our entire local neighborhood falling toward the gravitational center of this vast structure, much like water flowing downhill into the deepest valley. But the story does not end there. As our maps have improved, we've learned that the pull of the Laniakea supercluster is itself part of an even grander flow. The Great Attractor seems to be just a waypoint on a much longer journey. The entire Laniakea supercluster, including us, is being pulled toward an even more massive and distant concentration of mass known as the Shapley supercluster. the largest known structure in our local universe. This reveals a universe that is not uniformly expanding. On the largest scales, the Hubble flow, the general expansion of space, is overlaid with these subtle rivers of motion, where the gravity of immense superclusters creates deviations, tugging galaxies off their purely expansionary paths. Studying these flows is like being a hydrologist tracing the subtle currents of a vast ocean, allowing us to map the distribution of mass, both seen and unseen, across the cosmos. The Great Attractor, therefore, is more than a destination. It is a profound clue. Its gravitational pull helps cosmologists weigh the dark matter in our local universe, confirming that the invisible scaffolding of the cosmos is arranged in an intricate, hierarchical web, with our galaxy caught in its gentle, but irresistible, current. From the immense, slow gravitational currents that pull entire superclusters of galaxies, we now turn to a cosmic phenomenon that operates on the opposite end of the spectrum, blindingly fast, incredibly powerful, and frustratingly brief. Discovery number 19 introduces one of the most enigmatic puzzles in modern astronomy: fast radio bursts, or FRBs. Imagine a flash of radio waves, a blast of energy so intense that in just a millisecond, the blink of an eye, it can release more energy than our sun emits over several days. These are not slow, steady signals. They are cosmic screamers appearing suddenly from random directions in the sky, lasting for a fleeting instant, and then vanishing without a trace, often never to be repeated. For years after the first one was discovered in archival data in 2007, astronomers debated whether these signals were even real or just some bizarre glitch in the data. But as detection methods improved, more and more were found, confirming that FRBs are a genuine and profoundly mysterious feature of our universe. The central mystery lies in their origin. What natural cosmic engine could possibly produce such an enormous amount of energy and focus it into such an incredibly short burst? The search for an answer has led to a fascinating zoo of theories. The most promising and widely accepted explanation points to magnetars. These are a special type of neutron star, the ultra-dense, collapsed core of a massive star that went supernova, but with an added twist. A magnetar possesses a magnetic field that is trillions of times more powerful than Earth's. This magnetic field is so strong it could erase a credit card from half the distance to the moon. Theorists suggest that these magnetic fields can become twisted and strained, building up immense stress. When the crust of the neutron star suddenly cracks in a starquake, or when magnetic field lines snap and reconnect, it could unleash a titanic blast of radio waves in a fraction of a second, creating the signal we detect as an FRB. In recent years, astronomers have indeed detected FRBs originating from known magnetars within our own galaxy, providing the first solid link between a specific type of object and these bursts. This was a major breakthrough, suggesting that at least some FRBs have a natural, if extreme, explanation. However, the mystery is far from completely solved. While some FRBs are one-off events, others are repeaters, flashing from the same location in the sky multiple times. This repeating nature rules out cataclysmic, one-time events like the collision of two neutron stars, which would destroy the source. It also opens the door to more exotic possibilities. Could some repeater signals be generated by a highly magnetized plasma stream, interacting with a companion star in a binary system? Or perhaps they are produced by a young, hyperactive magnetar moving through a dense cloud of debris left over from its supernova birth. And then there is the more speculative, though far less likely, hypothesis that cannot be ignored when discussing such structured, powerful signals: the possibility of an artificial origin. Could an advanced extraterrestrial civilization be generating these bursts for propulsion, communication, or some other technology far beyond our comprehension? While scientists consider this the least probable explanation, the universe is usually stranger and more creative than our fiction. The very fact that it remains a topic of discussion highlights just how extraordinary these signals are. Yet, the true value of FRBs may lie less in their mysterious source and more in their incredible utility as tools for probing the cosmos. As these bursts travel across billions of light years to reach us, they don't move through a perfect vacuum. They pass through the diffuse clouds of gas, dust, and plasma that float in the vast spaces between galaxies. This material, known as the intergalactic medium, is incredibly tenuous, far better than any vacuum we can create on Earth, but it still has an effect. It causes the radio waves to experience a phenomenon called dispersion. Lower frequency radio waves travel slightly slower through this plasma than higher frequency waves. So, when an FRB arrives at our telescopes, the highest frequency components get here first, followed by a cascade of progressively lower frequencies. By precisely measuring this delay, this dispersion measure, astronomers can calculate the total amount of ionized material the signal has encountered on its journey. This turns each FRB into a cosmic weighing scale. For decades, cosmologists have faced a problem. When they add up all the normal, or baryonic, matter they can see in stars, galaxies, and gas clouds, it only accounts for about half of the total amount of matter that should exist based on our models of the Big Bang. The rest of the normal matter is thought to be hiding in the form of a warm, hot intergalactic medium, a web of extremely diffuse, million-degree gas filament stretching between galaxies. This gas is so hot and thin that it's virtually invisible to our telescopes, but when an FRB passes through it, the dispersion effect betrays its presence. By analyzing the signals from many FRBs at different distances, astronomers can finally take a census of this missing matter. Early results are incredibly promising, suggesting that FRBs are indeed detecting this long-sought component of the universe's mass. What began as a perplexing mystery has rapidly evolved into a powerful new technique for mapping the invisible architecture of the cosmos, allowing us to literally weigh the unseen threads that connect the galaxies in the great cosmic web. Yet, as we use these fleeting cosmic flashes to map the present-day universe, we stumble upon a discrepancy that strikes at the very heart of modern cosmology, a puzzle so persistent it has become one of the most talked-about topics in astronomy. This is discovery number 20, a problem known as the Hubble tension. At its core is a single, deceptively simple number, the Hubble constant. This value represents the current rate at which the universe is expanding, the speed at which galaxies are receding from us for each million parsecs of distance. Measuring this number accurately is arguably the most crucial task in cosmology, as it tells us the universe's age, its size, and its ultimate fate. For decades, astronomers have pursued this goal with two primary, highly precise methods. The shocking revelation is that these two methods, both considered extremely reliable, are now returning stubbornly different answers. The first approach looks back to the universe's infancy, to the cosmic microwave background we discussed earlier. Satellite missions like Planck have mapped the CMB with extraordinary detail. By analyzing the subtle patterns in this ancient light, the size and distribution of the hot and cold spots cosmologists can work out the ingredients of the early universe, the amounts of ordinary matter, and dark energy. Using our well-tested model of cosmic evolution, they can then run the simulation forward, calculating how this infant universe should have expanded over 13.8 billion years to arrive at its present state. This early universe method provides a very precise prediction for what the Hubble constant should be today. The second approach measures the expansion rate directly in our local, modern universe. This is the legacy of the supernova teams that discovered dark energy. Astronomers use objects they call standard candles, like Type 1a supernova or pulsating stars known as Cepheid variables. These objects have a known intrinsic brightness. By measuring how bright they appear from Earth, we can calculate their distance incredibly well. Then, by measuring how much the light from their host galaxies is redshifted stretched to longer wavelengths by the expansion of space. We get their velocity. Comparing distances and velocities for many galaxies gives us a direct, empirical measurement of the Hubble constant right now. The problem, the tension, is that these two numbers do not agree. The early universe measurement from Planck suggests a slower expansion rate, while the local universe measurements from supernova and other indicators consistently point to a faster one. The difference is not large, only a few percent. But the uncertainty in each measurement has shrunk so much that the gap is now statistically significant, sitting at a confidence level of about 5 sigma. In the world of physics, that means there is only a 1 in a million chance that this discrepancy is a mere fluke. It is a real contradiction. Imagine two of the most accurate clocks in the world, both built by master watchmakers, but one consistently ticks slightly faster than the other. The difference is small, but it tells you that something fundamental is misunderstood about the mechanics of timekeeping itself. This is why the Hubble tension is so profoundly important. It strongly suggests that our standard model of cosmology, the incredibly successful lambda cold dark matter model that has been the foundation of our understanding for decades, might be incomplete. We could be missing a fundamental piece of physics. Perhaps dark energy is not a constant as we have assumed, but an energy field that has evolved over time, growing stronger in the recent universe, and thus giving expansion an extra push. Or maybe dark matter has properties we haven't accounted for. An ability to interact with itself or with radiation in a way that subtly alters the expansion history. Another possibility is the existence of a new, previously unknown type of neutrino or another relic particle from the Big Bang that would change the early universe's energy density, and thus the predicted expansion rate. Solving this puzzle is not just an academic exercise, it is a potential gateway to a revolution in physics. Every time in history that a persistent, small discrepancy has appeared between theory and observation, it has led to a monumental shift in our understanding. The slight anomaly in the orbit of Mercury pointed the way to Einstein's theory of general relativity. The Hubble tension could be our generation's Mercury, a tiny crack in an otherwise beautiful edifice that, when pried open, reveals an entirely new layer of reality. New space telescopes, like the recently launched James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, are dedicating significant observing time to remeasure the Hubble constant with even greater precision, using different methods to cross-check the results. They are not trying to prove one side right and the other wrong. They are trying to understand why the universe itself seems to be giving us two different answers to the same fundamental question. The resolution of the Hubble tension will either force us to patch our current model or, far more excitingly, guide us toward a new, deeper theory of the cosmos, one that finally explains the true nature of the dark components that shape our universe. While the Hubble tension presents a puzzle about the universe's present expansion, a new observatory has begun to peer directly into the deep past, seeking answers at the very dawn of time. This brings us to discovery number 21, a technological marvel that is already reshaping cosmology. The revolutionary first images from the James Webb Space Telescope. After decades of planning and a nail-biting launch and deployment, JWST opened its golden, segmented eye to the cosmos, and the results have been nothing short of breathtaking. Positioned 1 million miles from Earth at the gravitationally stable Lagrange point 2, this telescope is not merely an improvement on Hubble, it is a completely different kind of instrument. While Hubble primarily observed in visible and ultraviolet light, JWST is an infrared telescope designed to see the heat signatures of the universe. This capability is the key to its time-traveling power. Because the universe is expanding, the light from the most distant, ancient objects is stretched as it travels across the cosmos, shifting from visible wavelengths into the infrared part of the spectrum. JWST is uniquely equipped to catch this stretched, ancient light, allowing it to see further back in time than any telescope before it, to within a mere 200 million years of the Big Bang itself. The initial deep field image released in July 2022 was a stunning demonstration of this capability. It showed a patch of sky no larger than a grain of sand held at arm's length, yet it was filled with thousands of galaxies, a dizzying cosmic vista. Among these points of light were galaxies so distant that their light has been traveling for over 13.4 billion years to reach us. We are seeing them not as they are today, but as they were in their infancy. And this is where the first major surprise emerged. According to prevailing models of galaxy formation, the very first galaxies should have been small, messy, and inefficient at forming stars. They were thought to have taken billions of years to merge and grow into the majestic spiral and elliptical structures we see in the modern universe. But JWST revealed galaxies that appear shockingly mature, well-structured, and massive, existing at a time when the universe was only a few % of its current age. It's like looking at a photo album of a human and finding a fully grown adult in a picture taken just days after their birth. These galaxies seem to have formed far more rapidly and efficiently than our theories predicted, forcing cosmologists to seriously reconsider the timeline and processes of galaxy assembly in the early universe. This unexpected maturity is not the only challenge JWST has presented. The telescope's incredible sensitivity is also revealing a much larger number of bright galaxies in the early universe than most models anticipated. The cosmos, it seems, was bustling with activity much sooner after the Big Bang than we thought. Scientists are now actively exploring what could explain this rapid growth. Perhaps the early universe was seeded by much larger clumps of dark matter than previously believed, providing a stronger gravitational scaffolding for gas to collapse and form stars quickly. Or maybe the first stars themselves were fundamentally different, forming from pure hydrogen and helium without heavier elements to cool the gas efficiently, potentially leading to the creation of monstrously large stars that lived fast and died young, seeding their environments with the heavy elements needed for subsequent generations of stars and planets at an accelerated rate. JWST is not just providing answers, it is posing profound new questions that are driving a healthy and exciting revolution in astrophysics. Beyond rewriting the story of galaxy formation, JWST power extends to the study of worlds around other stars. One of its most anticipated roles is as an interstellar chemist, analyzing the atmospheres of exoplanets. When a planet transits or passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Different molecules in that atmosphere absorb specific wavelengths of light, leaving behind a unique chemical fingerprint. JWST infrared vision is perfectly suited to read these fingerprints. In some of its earliest exoplanet observations, the telescope detected the clear signature of water vapor, along with evidence of clouds and haze, in the atmosphere of a gas giant planet over 1,000 light-years away. This might seem like a confirmation of what we expected, but it's the precision and detail that are revolutionary. Future observations will target smaller, rocky planets in habitable zones, searching for combinations of gases that could be potential biosignatures, such as oxygen, methane, and carbon dioxide. The ability to characterize the air on another world marks a leap from simply detecting exoplanets to truly studying them as individual worlds with their own weather and chemistry. Furthermore, JWST is acting as a powerful microscope for the processes of stellar birth. Because infrared light can pierce through the dense clouds of gas and dust where stars are born, the telescope can see directly into the stellar nurseries that are hidden from optical telescopes like Hubble. Its first images of the Carina Nebula and the Pillars of Creation revealed hundreds of previously hidden newborn stars, their faint light no longer obscured by the cosmic dust. We can now study the very earliest stages of star formation, observing the swirling disks of material around young stars where planets are beginning to coalesce. By analyzing the complex organic molecules frozen in these disks, JWST is providing a direct window into the raw ingredients that go into making planetary systems, offering clues about how common the building blocks of life might be throughout the galaxy. The James Webb Space Telescope is more than just a new set of eyes on the universe. It is a time machine, a chemical analyzer, and a stellar midwife all in one, promising a decade of discoveries that will undoubtedly challenge our old assumptions and illuminate the deepest mysteries of the cosmos. As we contemplate the vast timelines of the cosmos, it's almost poetic to discover that some of the most precise timekeepers in the universe are the remnants of stellar death. This brings us to discovery number 22, the extraordinary phenomenon of pulsars. The story of their detection begins with a moment of delightful confusion. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a radio telescope she helped build when she noticed a curious, repetitive signal. It was a series of sharp, rapid pulses, arriving with such unwavering regularity that they stood out starkly against the random noise of the cosmos. The signal was so perfectly timed that Burnell and her supervisor, Anthony Hewish, half-jokingly labeled it LGM1 for Little Green Men, humorously entertaining the possibility of an artificial source. What they had actually stumbled upon was the first observed pulsar, a type of neutron star that behaves like a cosmic lighthouse. A neutron star is the incredibly dense core left behind after a massive star goes supernova. During this violent collapse, the star's core is compressed so powerfully that protons and electrons are forced together to form neutrons, creating a ball of matter so dense that a single sugar cube-sized amount would weigh as much as a mountain on Earth. But a pulsar is a neutron star with a special characteristic. It spins, and it spins incredibly fast. As the star collapses, it conserves its angular momentum, causing its rotation to accelerate dramatically, much like an ice skater pulling in their arms. A newborn pulsar can rotate hundreds of times per second. Coupled with this rapid spin is an immensely powerful magnetic field, trillions of times stronger than Earth's. This field funnels charged particles toward the star's magnetic poles, where they are accelerated and blasted out as intense beams of radiation. If the star's rotation axis is misaligned with its magnetic axis, these beams sweep through space like the beacon of a lighthouse. From our perspective on Earth, we see a brilliant flash of radio waves, visible light, or even X-rays each time the beam sweeps across our line of sight. This is the pulse that gives pulsars their name. The true marvel of these objects lies not just in their power, but in their phenomenal precision. The timing of these pulses is astoundingly regular, rivaling, and in some cases even surpassing the accuracy of the best atomic clocks here on Earth. This stability arises from the incredible rotational inertia of the neutron star. Its immense mass and compact size make it resistant to any forces that might cause it to wobble or slow down noticeably. This turned pulsars from a fascinating curiosity into one of nature's most useful tools. Their reliability was so renowned that when humanity sought to create a universal map pointing the way to Earth, we used pulsars as the coordinates. The plaques placed aboard the Pioneer 10 and 11 spacecraft, intended for any extraterrestrial intelligence that might find them, feature a diagram showing our solar system's position relative to 14 known pulsars. Each pulsar is represented by a line pointing toward it, with its unique pulse frequency engraved in binary code. Because a pulsar's spin slows down at a predictable rate over millions of years, an intelligent civilization could use these frequencies as a cosmic clock to determine not only where we are, but precisely when the spacecraft was launched. This practical application has only expanded with time. Today, astronomers are using networks of pulsars across the galaxy in an ambitious experiment known as a pulsar timing array. The concept is brilliantly simple. Gravitational waves, those ripples in spacetime caused by the collision of supermassive black holes, subtly warp the fabric of the cosmos as they pass through it. This warping minutely changes the distance between Earth and a distant pulsar. When a gravitational wave passes by, it might cause the pulse from a particular pulsar to arrive a few tens of nanoseconds early or late. By itself, this tiny shift is impossible to distinguish from other noise, but by meticulously monitoring the timing of dozens of millisecond pulsars, those that spin hundreds of times per second, across the galaxy over many years, scientists can look for a correlated pattern of timing deviations that would be the hallmark of a background hum of low-frequency gravitational waves. In recent years, several consortia have announced evidence for this very signal, opening a new low-frequency window onto the universe and allowing us to listen to the chorus of merging supermassive black holes throughout cosmic history. Looking to the future, pulsars offer a potential solution to one of the great challenges of deep space travel: navigation. Once a spacecraft ventures far from Earth, traditional methods like GPS become useless. But pulsars are visible across the galaxy, and their predictable pulses are like regularly ticking clocks placed at known positions in the sky. By comparing the arrival times of pulses from multiple pulsars, a spacecraft could triangulate its position in the galaxy with phenomenal accuracy, creating a kind of cosmic GPS system that would work anywhere, even on an interstellar journey. NASA has already tested this concept with experiments on the International Space Station, demonstrating that X-ray pulses from certain pulsars can be used to determine a vessel's location autonomously. This vision of pulsar-based navigation transforms these celestial lighthouses from mere subjects of study into active guides, beacons that could one day help humanity find its way through the vast ocean of space, using the steady, reliable heartbeat of dead stars to chart a course to the stars. And yet, for all our sophisticated tools searching for the natural rhythms of the cosmos, like pulsars and gravitational waves, one of the most compelling moments in the history of astronomy came from a signal that was profoundly unnatural. Discovery number 23 takes us back to a warm summer night in 1977, to the Big Ear Radio Telescope in Ohio, and to a burst of data so extraordinary that it inspired the single most famous annotation in science, the WOW signal. For decades, the search for extraterrestrial intelligence, or SETI, had been scanning the skies, hoping to find a signal that stood out from the natural background noise of the universe. The assumption was simple. If an advanced civilization wanted to announce its presence, it might use a powerful, focused beacon, and the most logical frequency to use would be the radio emission line of neutral hydrogen at 1420 MHz. This is a quiet channel in the cosmic symphony, a natural watering hole, where any technologically adept species might think to listen or to call out. On August 15th, the Big Ear Telescope was patiently listening, and for exactly 72 seconds, its receivers recorded something breathtaking. The signal rose in intensity, peaked, and then faded away, following a perfect bell curve exactly as you would expect from a distant, fixed source passing through the telescope's stationary beam. When volunteer astronomer Jerry Amon reviewed the computer printout days later, his eyes were drawn to a string of alphanumeric codes representing the signal's strength. The sequence was 6 = QU = 5. In the telescope's notation, this meant an intensity so strong it went off the charts. Circling the code, Amon scribbled the now legendary exclamation, "Wow!" In the margin, this wasn't just a blip. It had all the hallmarks of an artificial interstellar broadcast. It was narrowband, meaning it was focused on one specific frequency, unlike the broad-spectrum noise from natural sources like quasars or pulsars. It appeared to originate from a point in space, not a wide area, and it was incredibly powerful. In short, it was exactly what SETI scientists had been hoping to find. The immediate and enduring mystery of the WOW signal is that it was never heard again. Despite numerous attempts by Eamon and others to re-observe the same patch of sky in the constellation Sagittarius, the signal remained stubbornly silent. This singular, unrepeated nature is the core of its intrigue. What could have caused it? The most tantalizing possibility is, of course, an extraterrestrial transmission. Perhaps it was a one-time beacon from a distant civilization, sweeping across our solar system for that brief 72-second window before moving on. Maybe it was an incredibly powerful radar signal from an alien spacecraft, or a communication directed at someone else that we just happened to intercept. The signal's characteristics make a convincing case against most known natural explanations. It wasn't a satellite or a passing aircraft, as those would have been moving relative to the stars and would have caused a different frequency shift. It wasn't a reflection of a human signal off a piece of space debris, as no terrestrial broadcast at that exact frequency was known at the time. For a signal to be so strong and then vanish completely suggests a transient, one-off event, which deepens the mystery rather than solves it. The legacy of the WOW signal is far greater than the event itself. It became a cultural touchstone, a symbol of the very real possibility that we are not alone. It injected a shot of adrenaline into the SETI community, proving that their search was not in vain, that the universe was capable of producing a signal that perfectly matched their criteria. It forced a serious conversation about the practical challenges of SETI. If a signal is truly transient, how do we ensure we don't miss the next one? This led to the development of more sophisticated, multi-telescope arrays that can observe larger swaths of sky continuously, hoping to catch a follow-up signal if another WOW event occurs. The signal also highlighted the needle in a haystack problem. The sky is vast, and we can only listen to a tiny fraction of it at any given time. The WOW signal could have been a continuous broadcast from a single star, and we simply listened for the wrong 72 seconds over the last 47 years. Ultimately, the WOW signal occupies a unique space in science. It is not proof of extraterrestrial intelligence, but it is the best example we have of a signal that we cannot convincingly explain as natural. It is a ghost in the machine of cosmology, a persistent reminder of how little we know and how much there is to discover. It embodies the essence of the scientific quest, a moment of stunning discovery followed by decades of rigorous, frustrating inquiry. The signal's power lies in its ambiguity. It keeps the door to the cosmos wide open, fueling our imagination and driving the continued search. It asks a question that we are still trying to answer, a question whispered across the light years on a quiet night in 1977, a question that continues to echo in every new scan of the heavens: was that really you? While we search the cosmos for signals and structures, sometimes the most profound discoveries are defined not by what is there, but by what is startlingly absent. This leads us to discovery number 24, a finding that redefines the meaning of empty space, the staggering void in Boots. Imagine a region of the universe so vast that it spans 1 billion light-years, a volume of space that could contain thousands of galaxies like our Milky Way. Now imagine that within this colossal expanse there are almost none. This is not a metaphor for a sparsely populated area. It is a true cosmic desert, a near-perfect vacuum on a scale that challenges our very comprehension. The Boots Void, discovered in the 1980s during large-scale galaxy surveys, is one of the largest known structures in the universe, and its defining feature is its overwhelming emptiness. This discovery directly confronts our prevailing model of the cosmos, which is built upon the concept of the cosmic web. According to this model, the distribution of matter in the universe is not random, but forms an intricate, interconnected pattern. Galaxies are not scattered like isolated islands. They are strung along vast filaments of dark matter, like pearls on a necklace. These filaments stretch across the cosmos, connecting at dense nodes where massive galaxy clusters reside. Between these brilliant strands and knots are the voids, the empty spaces in the web. However, cosmologists expected these voids to be relatively small, perhaps 100 million light-years across. The existence of a void as immense as the one in Boots, 1 billion light-years in diameter, was completely unexpected. It is like finding a hole in a spider's web that is larger than the web itself. Its sheer size suggests that our understanding of how matter clumped together in the early universe may be missing a crucial piece of the puzzle. So how could such an enormous nothingness come to be? The leading theory points back to the primordial seeds of structure we see in the cosmic microwave background. Those tiny fluctuations in the early universe were the blueprints for everything that followed. The Boots void likely started as an unusually large underdense region in that primordial plasma, a place where there was slightly less matter than the cosmic average. As the universe expanded over billions of years, gravity acted as the great sculptor. In the denser regions, gravity pulled matter together, forming galaxies and clusters. But in the underdense region, the opposite occurred. The gravitational pull of the surrounding denser filaments and clusters actually tugged matter out of the void, causing it to evacuate further. It's a process akin to a cosmic tide. The void didn't just stay empty, it became emptier over time as the universe grew. Its contents steadily drained away by the gravitational attraction of its denser neighbors. This is where the enigmatic force of dark energy enters the story. While gravity works to pull matter together, dark energy drives the expansion of space itself. In the crowded regions of the cosmic web, gravity is the dominant force, fighting a tug-of-war against dark energy's outward push. But inside a vast void like Boots, where there is very little matter, gravity is exceptionally weak. Here, dark energy operates unopposed. The expansion of space within the void is not slowed by the collective gravity of galaxies, allowing the void to expand faster than the universe as a whole. The existence of such a colossal emptiness provides a unique natural laboratory for studying the effects of dark energy. By measuring how the void grows over time, astronomers can gain insights into the strength and nature of this mysterious force that governs the ultimate fate of the cosmos. The profound implication of the Boots void is that emptiness is not passive. It is an active and dynamic component of the universe's architecture. These voids are not simply the blank spaces between the interesting parts. They are fundamental to the overall shape and evolution of the cosmic web. Their growth influences the motion of entire galaxy clusters, subtly tugging them in ways that add another layer of complexity to the large-scale flow of matter. The void challenges us to expand our perspective. We often focus on the bright, dense objects, the stars, galaxies, and clusters, but the emptiness between them holds its own profound secrets. The Boots void is a monument to absence, a billion light-year-wide reminder that in the cosmos, what is not there can be just as important and just as illuminating as what is. Yet, even as we map the vast emptiness of intergalactic space, the hunt continues within our own cosmic backyard, driven by a set of gravitational clues that point to a possibility as thrilling as any distant void. Our 25th discovery takes us back to the familiar darkness beyond Neptune, but this time with a tantalizing twist: the potential for a true, undiscovered giant planet lurking in the solar system's frozen fringe. This isn't a reclassification of a known world like Pluto. This is the active pursuit of a massive, hidden member of our Sun's family, a world provisionally dubbed Planet 9. The evidence for its existence is not a direct image or a fleeting glint of sunlight, but something far more subtle and compelling: the strange, clustered orbits of small, icy bodies in the distant Kuiper belt. Astronomers studying these extreme trans-Neptunian objects noticed something bizarre. A group of them, with orbits that take thousands of years to complete, share a peculiar orbital alignment. Their elongated paths are tilted in similar ways, and their points of closest approach to the Sun, their perihelia, seem to be grouped together in space. This is highly unusual. The gravitational influence of the known giant planets, especially Neptune, should have randomized these orbits over billions of years. It is as if you dropped a handful of marbles on a large, flat sheet, and they all rolled not in random directions, but consistently toward one specific corner. The simplest explanation is that the sheet isn't flat. It's tilted by an unseen mass. In the same way, the most elegant solution for the orbital oddities in the Kuiper belt is the gravitational shepherding of a planet several times more massive than Earth, on a wide, slow orbit far beyond Pluto. The hypothetical properties of this world are staggering. Based on the gravitational pull needed to create the observed clustering, Planet 9 is estimated to have a mass between 5 and 10 times that of Earth, placing it in the category of a mini-Neptune or a super-Earth, a type of planet common around other stars but missing from our own solar system's inventory. Its orbit would be immensely elongated, taking it on a 10,000 to 20,000-year journey around the Sun. At its closest approach, it might be within a few hundred astronomical units, but at its most distant, it could swing out over 1,000 O into the deep freeze. For context, Pluto is only about 40 O from the Sun. This proposed planet would spend most of its time in the profound darkness of the outer solar system, its faint reflected sunlight making it incredibly difficult to detect. The search for this ghost world is a monumental technological challenge, a cosmic game of hide and seek on the grandest possible scale. Astronomers are not simply pointing telescopes at the sky and hoping to see a moving dot. They are using some of the most powerful observatories on Earth, like the Subaru telescope in Hawaii, which has a wide enough field of view to scan large patches of the predicted orbital path. The process involves taking images of the same section of sky over several nights, and looking for any object that has moved just a tiny fraction against the backdrop of infinitely distant stars. It is painstaking, needle-in-a-haystack work, compounded by the fact that the planet's exact position is unknown. We only have a rough map of where it might be. Adding to the difficulty at such immense distances, the planet would be exceptionally faint, and its motion across the sky would be agonizingly slow, perhaps moving only a few arcseconds per hour. The implications of a confirmed discovery would be nothing short of revolutionary. First and foremost, it would be the first new true planet satisfying the orbital dominance criteria that reclassified Pluto discovered in our solar system in modern times. This would be an epoch-making event, instantly rewriting every textbook diagram of our cosmic neighborhood. But beyond the sheer excitement of the find, Planet 9 would solve numerous solar system mysteries. Its gravitational influence could explain not only the peculiar orbits of the distant Kuiper belt objects, but also why the average plane of the solar system is tilted by about 6 degrees relative to the Sun's equator. A distant, massive planet could have torqued the entire system over billions of years. Its existence would also force a re-evaluation of our models of planetary formation. How did a planet of that size end up so far away? The leading theory suggests it may have formed closer to the Sun, in the region of the gas giants, before a gravitational encounter with Jupiter or Saturn flung it out into a distant, eccentric orbit, a dramatic event in our solar system's early history. Finding Planet 9 would not just be about adding a new world to a list. It would provide a master key to understanding the dynamic and often violent processes that shaped our entire planetary system, revealing a chapter of our history that has been hidden in the darkness until now. From the silent, gravitational tugs of a potential hidden planet, we now turn to the universe's most violent and explosive tantrums. Discovery number 26 forces us to confront the raw power of gamma-ray bursts, or GRBS. If you were to compile a list of the most energetic events since the Big Bang itself, GRBS would undoubtedly hold the top spots. For a fleeting few seconds, A single gamma-ray burst can outshine every star in 100 billion galaxies combined, releasing more energy than our Sun will emit over its entire 10 billion-year lifetime. These are not mere stellar flares or supernova. They are cosmic detonations of almost incomprehensible ferocity, and for decades, they were one of astronomy's greatest secrets, detected not by optical telescopes, but by classified military satellites designed to monitor for nuclear weapons tests in space. The story of their discovery is a fascinating tale of Cold War intrigue. In the 1960s, the United States launched the Vela satellite series to ensure compliance with the Nuclear Test Ban Treaty. Their job was to look for the telltale flash of gamma radiation that would signal a clandestine atomic explosion in the atmosphere or in space. To their surprise, the satellites began detecting powerful bursts of gamma rays, but they were not coming from Earth. They were originating from deep space, distributed randomly across the sky. For years, this data was kept secret, as analysts struggled to understand its origin. Were they from within our solar system, from our galaxy? It wasn't until the data was declassified and studied by astronomers that the true, extragalactic nature of these bursts was confirmed, revealing a universe far more violent and unpredictable than anyone had imagined. We now understand that there are two primary types of these cosmic blasts, each with a different, cataclysmic origin. Long-duration gamma-ray bursts, which last for more than 2 seconds, are thought to be the birth cries of black holes. They occur when a star dozens of times more massive than our Sun exhausts its nuclear fuel. Without the outward pressure from fusion to support it, the star's core collapses instantly, forming a black hole. The outer layers of the star, now without a foundation, plummet inward. But not all of this material falls into the abyss. Some of it is funneled by intense magnetic fields into powerful jets that erupt from the star's poles at over 99.99% the speed of light. If one of these jets is pointed directly at Earth, we see it as a long gamma-ray burst, a brilliant beacon announcing the death of a giant and the birth of a monster. Short-duration bursts, lasting less than 2 seconds, are believed to be the result of a different, yet equally spectacular, cosmic dance, the merger of two neutron stars or a neutron star and a black hole. As these incredibly dense objects spiral into each other, they also generate powerful jets of radiation, creating a shorter, but equally intense, flash. While these events are spectacular to observe from a safe distance, the truly sobering discovery is what would happen if one occurred too close to home, and with its jet aimed directly at our planet. A gamma-ray burst within our own galaxy, pointed at Earth, would be a civilization-ending event. The initial blast of gamma rays themselves would not incinerate the surface, they would mostly interact with the upper atmosphere. But that interaction would trigger a chain reaction of destruction. The gamma rays would smash into air molecules, breaking apart nitrogen and oxygen and initiating a chemical process that produces vast quantities of nitrogen dioxide, a brownish, toxic gas. This gas would act like a sunblock, but for the entire planet, absorbing sunlight and plunging the Earth into a rapid, dramatic cooling, a kind of cosmic winter. The most devastating long-term effect, however, would be on the planet's protective shield, the ozone layer. The gamma rays would rip apart ozone molecules, depleting the layer that protects all surface life from the sun's harmful ultraviolet radiation. The aftermath would be a biological catastrophe. With the ozone layer severely damaged or destroyed for several years, the surface would be bombarded by intense, mutagenic UVB and UVC radiation. This would cause widespread sunburns in animals and damage the DNA of phytoplankton in the oceans, the base of the marine food web. Crop failures would be widespread as plants withered under the increased radiation. The combination of a dimmed, cooled planet and a surge in ultraviolet light could easily trigger a mass extinction on a scale comparable to the event that wiped out the dinosaurs. In fact, some scientists have speculated that a gamma-ray burst, perhaps from a dying star within 6,000 light-years, could have been responsible for the Ordovician mass extinction 440 million years ago, which wiped out over 85% of marine species. The evidence is circumstantial, but the terrifying possibility remains. This discovery transforms our understanding of planetary habitability. It introduces the concept of a galactic habitable zone. A planet needs more than just to be in the right spot around its star. It also needs to be in the right neighborhood within its galaxy. Regions near the galactic core, where stars are densely packed and stellar deaths are more frequent, might be far more dangerous. Gamma-ray bursts could effectively sterilize large swaths of a galaxy, resetting the evolutionary clock and making the development of complex, long-lived life more challenging. Our own solar system, situated in a quieter suburban region of the Milky Way between two spiral arms, might enjoy a period of relative cosmic peace, but we are not immune. The importance of monitoring the sky for these events has never been clearer. Missions like NASA and Neil Gehrels' Swift Observatory and the Fermi Gamma-ray Space Telescope act as our early warning system, constantly scanning the heavens for these flashes of doom. While we cannot stop a gamma-ray burst, understanding their frequency and distribution helps us assess the long-term risks to life on Earth and appreciate the fragile, fortunate set of circumstances that has allowed our civilization to flourish in a seemingly peaceful cosmos. A peace that could be shattered in an instant by a death scream from a star halfway across the galaxy. But sometimes, the most profound discoveries in space aren't about distant galaxies or exotic particles. They come from watching our own creations as they journey into the void, noticing when they drift ever so slightly off course. This brings us to discovery number 27, a mystery that captivated physicists for over 2 decades, the Pioneer anomaly. In the early 1970s, humanity sent 2 ambassadors on a one-way trip to the stars, the Pioneer 10 and Pioneer 11 spacecraft. After completing their primary missions to Jupiter and Saturn, they continued on trajectories that would eventually carry them out of the solar system. As they traveled, scientists meticulously tracked their positions using the Deep Space Network, measuring their velocity with incredible precision by analyzing the Doppler shift in their radio signals. Over time, a tiny, baffling inconsistency emerged. Both spacecraft were experiencing a minuscule, constant deceleration back toward the Sun, a sunward tug of about 10 billion times weaker than the gravity we feel on Earth's surface. It was an almost imperceptible drift, equivalent to the gravitational pull of a single snowflake, but it was persistent, unexplained, and it affected both identical probes. For years, this anomaly was a thorn in the side of physicists. Could this be a sign of new physics? Was our understanding of gravity, as described by Einstein's general theory of relativity, incomplete on the scale of the solar system? Perhaps there was some unknown form of matter or energy exerting a drag force, or maybe even a subtle flaw in the laws of gravity itself that only became apparent over vast distances. The Pioneer anomaly became a classic example of a scientific puzzle, a discrepancy between observation and theory that refused to go away. It demonstrated a fundamental principle of exploration. Sometimes, the act of sending a probe into the unknown doesn't just reveal secrets about the destination. It can also reveal hidden truths about the journey itself, or even about the probe we built to undertake it. The solution, when it finally came, was not found in rewriting the textbooks of cosmology, but in the painstaking discipline of engineering and computer modeling. A team of researchers embarked on a monumental effort to reconstruct the thermal properties of the decades-old spacecraft. They realized that the Pioneers were powered by radioisotope thermoelectric generators, which produced heat as a byproduct of radioactive decay. This heat had to be dissipated to prevent the spacecraft from overheating. The probes were designed to radiate this waste heat away into space. Crucially, the heat was not emitted perfectly evenly from all surfaces. More heat was radiated from the rear of the spacecraft, the side facing away from the direction of travel where the power systems were located. This created a tiny but continuous thrust. According to the simple physics of radiation pressure, every photon carrying away that heat also carried a minuscule amount of momentum. The net effect of more photons pushing off the back of the probe than the front was a very slight force pushing back toward the Sun, exactly matching the observed anomalous acceleration. The mystery wasn't a failure of gravity. It was the spacecraft literally pushing itself backwards with its own heat. The resolution of the Pioneer anomaly is a testament to the power of meticulousness. It underscores that in the extreme precision of deep space navigation, there is no such thing as an insignificant detail. The way a spacecraft manages its waste heat, the reflectivity of its paint, even the way its antenna is oriented, all of these factors can have measurable effects over years and billions of miles of travel. This lesson is now directly applied to modern missions. For a probe like NASA's, New Horizons, which flew past Pluto, engineers meticulously model the thermal radiation pressure from the spacecraft and account for it in their navigation calculations. What was once an unexplained anomaly is now a standard, predictable factor in flight dynamics. The story of the Pioneer anomaly serves as a powerful reminder that some of the most important discoveries aren't about finding something new out there, but about understanding the tools we use to explore with unprecedented accuracy. It shows that the universe often reveals its secrets not in grand pronouncements, but in whispers, and that we must learn to listen to even the faintest of signals if we are to truly understand our place in the cosmos. While the discovery of dark energy revealed an acceleration happening now, and the Hubble tension questions our precise understanding of that expansion rate, there is a theoretical framework that tackles the very first moments of the cosmos, a period of such incredible violence that it sets the stage for everything that follows. Our 28th discovery is the theory of cosmic inflation, a concept proposing that the universe underwent a breathtaking growth spurt in the first fraction of a second after the Big Bang. To grasp the scale of this event, imagine the entire observable universe, all hundreds of billions of galaxies spanning over 90 billion light-years, starting out smaller than a single proton. Then, in an almost incomprehensibly brief interval, from about 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, it expanded exponentially, doubling in size at least once every 10 to the negative 37 seconds, inflating to about the size of a grapefruit before transitioning to the more sedate expansion we see today. The primary motivation for this radical idea was to solve several major puzzles that the standard Big Bang theory left unanswered. The first is the horizon problem. If you look at the cosmic microwave background radiation coming from opposite sides of the sky, those two regions are so far apart that, in a universe expanding at a constant rate, light would not have had enough time since the Big Bang to travel between them. They should never have been in contact, never had a chance to reach the same temperature, and yet, the CMB is perfectly uniform to about 1 part in 100,000. It's as if you walked into a vast room where everyone had instantly agreed on the exact same thermostat setting without ever speaking to each other. The theory of inflation solves this by suggesting that these distant regions were indeed in causal contact before inflation began, when the entire universe was a tiny, interconnected speck. The inflationary burst then stretched this small, thermally equilibrated region into the vast cosmos we see, preserving that uniformity across distances that would otherwise be unreachable. The second puzzle is the flatness problem. Observations of the CMB tell us that the universe is geometrically flat on the largest scales, meaning parallel lines will never meet. For the universe to be so perfectly flat today, its density in the first moments would have had to be fine-tuned to an astonishingly precise value. Any tiny deviation from this critical density would have been magnified by billions of years of expansion, resulting in a universe that either quickly collapsed back on itself or expanded into a near-total vacuum. Inflation acts as a cosmic iron, smoothing out any initial curvature. Think of the surface of a balloon. When it's deflated, its surface can be wrinkled and curved. But as you inflate it to an enormous size, any small section of its surface appears flatter and flatter. In the same way, the inflationary expansion stretched the fabric of spacetime so dramatically that any initial curvature became negligible, resulting in the flat universe we measure. But perhaps the most profound implication of inflation is not just what it smooths, but what it amplifies. According to quantum mechanics, empty space is not truly empty. It is a seething foam of virtual particles popping in and out of existence. These are tiny quantum fluctuations in energy fields. Inflation proposes that during its exponential expansion, these microscopic quantum jitters were stretched to astronomical sizes. The slightly denser regions in this quantum foam served as gravitational seeds. After inflation ended, the normal expansion of the universe took over, and gravity got to work on these seeds. Over billions of years, it pulled more and more matter into the denser spots, eventually forming the first stars, galaxies, and the vast cosmic web of clusters and superclusters that we see today. This is a truly breathtaking connection. The largest structures in the universe, galaxies and clusters spanning millions of light-years, originated from subatomic quantum fluctuations that were magnified by a period of hyper-expansion in the first instance of time. Inflation provides a direct link between the realm of the incredibly small, governed by quantum mechanics, and the realm of the unimaginably large, governed by gravity. The strongest evidence for this extraordinary theory comes, once again, from the cosmic microwave background. The Planck satellite's exquisitely detailed map of the CMB's temperature variations shows a specific pattern, a particular distribution of hot and cold spots of certain sizes, that matches the predictions of inflationary models with remarkable precision. These patterns are the fossilized imprint of those primordial quantum fluctuations, stretched across the entire sky. Furthermore, inflation predicts a specific type of remnant that was also detected: primordial gravitational waves. The violent, rapid stretching of spacetime during inflation would have generated ripples in the fabric of the cosmos, a background hum of gravitational waves. While these have not been directly observed yet, their indirect signature is believed to be imprinted in the polarization pattern of the CMB light, a faint but specific swirl known as B-mode polarization. The hunt for this definitive signal is one of the most active frontiers in cosmology. The theory of cosmic inflation, while still a framework with different competing models, has so successfully explained the large-scale features of our universe that it has become the leading paradigm for understanding our cosmic origins, transforming the Big Bang from a simple idea of a hot, dense beginning into a dynamic narrative of quantum physics writ large across the entire heavens. But after counting down so many discoveries that make the universe feel alive with possibility, from hidden oceans to cosmic chemicals, we arrive at a question that hangs over all of them like a profound silence. This is discovery number 29, a puzzle so compelling it is known simply as the Fermi Paradox. It begins with a simple, almost casual question famously attributed to the physicist Enrico Fermi during a lunchtime conversation in the 1950s. Looking at the staggering scale of the universe, the hundreds of billions of stars in our galaxy, many billions of years older than our Sun, and the high likelihood that a significant number of them host Earth-like planets, the logical conclusion is that the galaxy should be teeming with life. Given enough time and material, intelligence should have arisen many times over, and if even a tiny fraction of those civilizations developed advanced technology and a desire to explore, the galaxy should have been colonized many times over by now. As Fermi put it, where is everybody? The paradox is the stark contradiction between the high probability of extraterrestrial intelligence and the complete, unsettling lack of any observable evidence for it. Our telescopes hear no engineered signals, our sky shows no signs of massive engineering projects, and no visitors have ever called. One of the most gripping frameworks for answering this question is the concept of the Great Filter. This idea suggests that the evolution of life from its genesis to a space-faring, galaxy-colonizing civilization must pass through a series of evolutionary and technological stages. The Great Filter is a barrier, a step in this process that is so improbably difficult that it effectively prevents almost all life from progressing beyond it. The terrifying implication of this theory lies in its timing. If the filter is behind us, meaning it was a step that life on Earth somehow managed to overcome against all odds, then we might truly be alone, or at least among the very first. Perhaps the spontaneous origin of life itself is the filter, an event so chemically improbable that it has only happened once in the observable universe. Or maybe the leap from simple prokaryotic cells to complex eukaryotic cells, which took over 2 billion years on Earth, is the real bottleneck. If we have already passed through the filter, it would explain the silence. We are the rare success story. The far more unsettling possibility is that the Great Filter lies ahead of us. This would mean that the development of intelligent, technological life is actually quite common, but that something inevitably happens to prevent that life from surviving long enough to become interstellar. The filter in this scenario could be self-destruction. Perhaps every advanced civilization, upon discovering the technologies that come with energy-intensive industry, eventually discovers the means of its own annihilation, whether through nuclear war, runaway climate change, or a biotechnology mistake. Or the filter could be an external event, like the gamma-ray burst we discussed, which periodically sterilizes large sections of the galaxy. If the filter is in our future, then the silence of the cosmos is a grave warning, a sign that no one makes it through the technological adolescence we are currently experiencing. The empty sky would then be a cosmic graveyard, filled with the ghosts of civilizations that flared up brightly and then went dark. Other solutions to the paradox require us to think beyond our own biological and technological limitations. Perhaps advanced civilizations are nothing like we imagine. Our searches, like SETI, assume that others would communicate using radio waves, a technology we mastered in the 20th century. But a civilization just 1,000 years more advanced than us might view radio as we view smoke signals, a primitive, inefficient technology long since abandoned. They might communicate using neutrinos, or through manipulations of space-time we can't yet conceive of, making their conversations completely invisible to us. Another possibility is that they are present, but deliberately avoiding contact. This is the zoo hypothesis, or the planetary park idea. They might be observing us from a distance, following a strict non-interference policy to allow our civilization to develop naturally, much like anthropologists studying an uncontacted tribe. Or the motives of a truly advanced intelligence might be so alien that the concept of contact or colonization is meaningless to them. They might have transcended physical bodies, living as digital consciousnesses in simulated realities, with no interest in the external, material universe. The cosmos might be full of such beings, and we wouldn't know how to look for them because we're searching for something that resembles us. Ultimately, the Fermi Paradox forces a deeply introspective look at our own future. The silence is not just an astronomical data point, it is a mirror. It asks us to consider what kind of civilization we want to become. Will we be one that succumbs to a great filter, becoming just another silent data point in the galaxy? Or will we navigate the challenges of climate change, technological risks, and geopolitical strife to become a stable, long-term species? The paradox shifts the focus from "where are they?" to "where will we be in 1,000 years?" It suggests that the first sign of intelligent life we discover in the universe might not be an alien signal, but our own reflection, as we learn to overcome the challenges that have kept the cosmos quiet. The Great Silence is not an answer, but a question, one that we must answer for ourselves through the choices we make here on Earth. And so we arrive at the 30th and final discovery on our list, one that is profoundly different from all the others. It is not a new particle, a distant galaxy, or a law of physics. Instead, it is a transformation of the human mind, a cognitive shift experienced by those who have ventured beyond our atmosphere. This is the overview effect, a term coined by author Frank White to describe the profound and often life-altering experience of seeing the Earth from space. While telescopes and probes have expanded our knowledge of the cosmos, the overview effect represents an inward discovery, a philosophical revelation with the tangible power to reshape our relationship with our home planet and with each other. Astronauts from many nations and backgrounds report a strikingly consistent set of feelings upon seeing the Earth suspended in the black void of space. The world they left behind, with all its conflicts, borders, and divisions, suddenly appears as a single, breathtakingly beautiful, and fragile oasis. The planet reveals itself not as a collection of separate countries, but as a unified, complex system. The atmosphere, which from the surface seems so vast, is seen as a shockingly thin, glowing blue veil, a delicate membrane protecting all known life from the harshness of space. This perspective triggers a deep, emotional understanding of planetary interconnectedness. As astronaut Ron Garan described it, it's like seeing the world from the outside and realizing that we are all traveling together on a spaceship Earth, sharing the same limited resources and facing the same ultimate fate. This isn't an intellectual concept learned from a book. It is a visceral, overwhelming insight that rewires one's perception of reality. The potential of this psychological discovery to change life on Earth is immense. The overview effect directly fosters a global consciousness, a sense of shared identity that transcends national, cultural, and political boundaries. From orbit, there are no lines on the map. You do not see the disputes over territory that have defined so much of human history. You see continents, oceans, and weather patterns, a living, breathing planet that is indifferent to the arbitrary divisions humanity has imposed upon it. This realization creates a powerful impetus for international cooperation. The challenges that threaten our collective future, climate change, resource depletion, pandemics, are global in scale. They cannot be solved by any one nation acting alone. The overview effect provides the emotional and philosophical foundation for the kind of unified action that is necessary, highlighting that our survival and prosperity are fundamentally linked. This shift in awareness carries a heavy weight of responsibility. The vision of Earth's fragility instills a powerful urge to protect it. Astronauts often return with a renewed commitment to environmental stewardship, understanding that the planet's life support systems are finite and vulnerable. This isn't a vague environmentalism. It is a direct consequence of having seen with one's own eyes that there is no Planet B in any practical sense. The overwhelming beauty of the blue marble set against the infinite darkness creates a deep-seated desire to preserve that beauty for future generations. It transforms environmental protection from a political issue into a matter of simple, clear-eyed necessity for the survival of our civilization. The exciting development is that we are no longer reliant solely on the anecdotal reports of a few hundred astronauts. With the dawn of commercial spaceflight and virtual reality technologies, the essence of the overview effect is becoming more accessible. While nothing can truly replicate the experience of being in orbit, immersive simulations and the prospect of more people traveling to space offer hope that this perspective shift could ripple through a much larger segment of the population. Imagine a world where leaders in business, policy, and science could access even a fraction of this transformative viewpoint. It could fundamentally alter decision-making processes, prioritizing long-term planetary health over short-term gains. The overview effect, therefore, is more than just a fascinating psychological phenomenon. It is a catalyst. It is the universe's way of holding up a mirror to humanity, showing us both our stunningly beautiful home and our profound responsibility to care for it. In gifting us this perspective, space exploration has provided perhaps the most crucial discovery of all: the vision of a unified humanity, capable of achieving greatness not by conquering the stars, but by first learning to cherish and preserve the precious world we all share. As our journey through these 30 discoveries comes to a close, we are left with a profound realization that reverberates far beyond the realm of astronomy. The exploration of space is not a luxury or an abstract intellectual exercise. It is a vital, direct, and continuous pipeline of knowledge that is actively shaping the destiny of our species. Each revelation, from the water ice on the moon to the enigmatic pull of dark energy, is not locked away in an ivory tower. Instead, these findings are practical gifts from the cosmos, offering us tangible solutions, critical warnings, and a deeper understanding of our own existence. They demonstrate that by looking outward, we are ultimately looking inward, gaining the tools and the perspective needed to navigate the challenges of the 21st century and beyond. Consider the practical applications unfolding right now. The quest for fusion energy, the holy grail of clean power, is inspired by the processes that fuel the stars themselves. The study of extremophile organisms in the vacuum of space is revolutionizing biotechnology and medicine, leading to more robust vaccines and new ways to preserve biological materials. The principles of orbital mechanics are optimizing global supply chains and communication networks here on Earth. Even the development of planetary defense strategies, aimed at tracking asteroids that could threaten our world, transforms theoretical astrophysics into a global security imperative. These are not distant possibilities. They are active areas of research where cosmic knowledge is being translated into terrestrial progress, proving that investment in fundamental science yields dividends across every facet of our society. But this journey has also served as a sobering reminder of our fragility. The threats of solar storms and potential gamma-ray bursts underscore that we exist in a dynamic and occasionally violent cosmic neighborhood. Understanding these dangers is the first and most critical step toward building a resilient civilization capable of weathering celestial events that have reshaped life on Earth in the past. This awareness fuels our desire to become a multi-planetary species, not as an escape from Earth, but as a crucial backup plan for the long-term survival of humanity. The discoveries of potentially habitable moons and exoplanets are not just about finding new homes. They are about ensuring that the light of consciousness, which has flickered into being on our pale blue dot, is not so easily extinguished. They teach us that our future security depends on expanding our presence beyond the cradle of Earth. On a deeper level, these 30 discoveries have rewritten our origin story. We now know with certainty that the atoms that constitute our bodies were forged in the hearts of long-dead stars and scattered across the galaxy by planetary nebulae and supernova explosions. We are, quite literally, stardust that has become conscious, the universe's way of looking back at itself and beginning to understand its own workings. This cosmic connection erases any lingering sense of isolation and replaces it with a profound belonging. We are an integral part of an unfolding cosmic narrative that spans 14 billion years, participants in a grand story of transformation and emergence. This perspective humbles us, while simultaneously empowering us with the knowledge that we are the product of an ancient and magnificent process. Therefore, the call to action that emerges from this exploration is clear and urgent. We must choose to remain a curious species. We must continue to support the scientific endeavors, the telescopes, the space probes, and the brilliant minds dedicated to this pursuit. The greatest discoveries are still ahead of us: the potential detection of life on another world, the unraveling of the dark matter and dark energy mysteries, the final resolution of the Hubble tension that may reveal new physics. Supporting this quest is an investment in our own enlightenment and our long-term survival. But the call extends beyond funding and research. It is a personal invitation to each of us to cultivate a cosmic perspective in our daily lives. To look up at the night sky not as a distant curtain, but as an ocean of possibilities that is intrinsically linked to our future. It is an encouragement to embrace the overview effect from right where you stand, to see Earth as a fragile, interconnected system that requires our collective stewardship. The knowledge gained from space exploration is a cosmic gift, but it is one that comes with immense responsibility. Let us use these insights to build a future on Earth that is peaceful, sustainable, and worthy of the incredible cosmic journey that brought us here. The next chapter of this story is not written in the stars.